Good morning. अच्छा, good morning.
Hello.
शनिवारी.
Hello, check.
Sorry? ॲक्च्युली हे फक्त रिकॅप आहे, त्याची काही गरज नाही. तुम्ही ते हे करून टाका. हे घालतो मी म्हणजे आवाज येईल, कोणी ऑनलाईन असेल तर. Okay, 9:30, so let's start. Anyone did you leave back from the bus, people? बस में? ओके, पण गेस्ट हाऊस मध्ये कोणी राहिले नाही ना? गेस्ट हाऊस मधले सगळे आले. ओके, दॅट वॉज द क्वेश्चन. Good. So we'll start 9:30. That's what we agreed. We'll start with a small recap, and then I have a few requests. So we'll take only maximum of 10 minutes. Shrirang will talk for 2 minutes, and then the lecture will be by Pramod Zog sir. Last week we went through a lot of physics. As we discussed, quantum computing is a mixture of physics, chemistry, material science, engineering of various types. So if you get students who want to become coders, they have to wait for 10 more years until fault tolerant universal quantum computers are invented. This is not the job for somebody who only wants to do computer science. Even computer scientists have to look under the hood right now, which is why you went through the physics. You will have to, at the algorithmic level, look at, you will have to look at the physics. So this is a bit of a recap of the physics. We talked about particles. All particles are waves, and all waves are particles. That's the fundamental tenet of quantum mechanics. What was the dimensionality of wave function? Anyone remembers? Good. Yeah, in 1 dimensions, 1 upon root L, otherwise volume. Eigenfunctions, what do they give? They are associated with a measurement operator. When eigenfunction is operated by a measurement operator, you get the same function back, but with the eigenvalue. And everything in quantum mechanics is based on expectation value. We have operators. Gates are operators. Gates are represented also in a differential form, calculus form, and gates can also be represented as matrix form. So operator is a matrix, it can be written as a differential equation, and operators operate on gates, or operators are gates. So operators operate on qubit. This is how quantum computing is different from classical digital computing. And these are the same fundamental principles which are applied in sensing as well, as you've seen. Yes, we talked about Hermitian and unitary operators. So those are two types of operators operating in two different conditions. Expectation value tells you something like probability of finding the particle. It depends on what measurement you make. So expectation value of the X operator tells you the position. Expectation value of the momentum operator tells you the average of that particular momentum, most probable value. We talked about hydrogen atom. This was covered by Kshirsagar madam. The wave function, and we will convert this to LaTeX form, was written in a form, and this will be part of the notes as cheat sheet. But Kshirsagar madam wrote the solutions. She also, I think, plotted them for hydrogen atom as well as the particle in a infinite well, and in each case the number of solutions is infinite, and this is how life is different from Bohr's atom. So all the solutions are possible. There's no right or wrong solution. Each has a different probability of occurrence depending on environmental conditions. So the solution is written as a summation of all possible solutions. The wave function is written as a summation of all possible solutions with a multiplying coefficient. Zog sir talked about superposition, and this is spelling mistake, entanglement, and these are at the heart of quantum computing. This gives the power of multiple states being available for computation, as well as the fact that you can arrive at a solution by operating via a physical operator. So, translating that back, operators, operations, gates in quantum computing are physical entities. They are not just a mathematical construct. So, you will have to know, the programmer will have to know physics to go from an algorithm to the code, or go from a problem to an algorithm to a code. To take an example, the entire field of quantum computing came up because the proposal was about studying molecules and atoms, which are physical entities to start with, which is why it was proposed that the computer itself should be tailored on a molecule, how molecule behaves quantum mechanically. And if it's a problem in optimization, our job is again to translate that optimization problem into an energy function, which Professor Zog called the Hamiltonian. And then nature knows how to minimize or maximize that Hamiltonian. So we use that trick, which is what we see in superposition, which is what we see in fringes in the two slit interference pattern, which is why that particular experiment is such an eye opener. Okay, so that was recap. Any questions on the recap? Anything that was not clear? More or less one important thing was done by Amit, where he actually laid bare one code, the Python code. So that was your first look at, or for some of you it was the first look at how the Python code works. What was striking? What was different about that code? Number of times you try, the solutions differ. Solutions differ. So every solution is a completely new simulation, and the simulation will not go to the same answer if you repeat the simulation. And that also told us more about how probability operates here. Yeah. Every eigenstate is a good solution, and depending on how many times you run the simulation, you can get a different eigenstate. The probability of every eigenstate depends on the coefficient, which is where all the physics and the mathematics of quantum computing is embedded. So the objective is to run it so many times that the coefficient becomes visible via a frequency distribution curve, a histogram, and then you get the solution. Okay, so then two separate announcements. We will continue classes on 16th. There could be an interaction with the Chief Minister online. We might have to go to a different room. 17th, 11 onwards, we will have a small recognition ceremony. Chandrakant Dada Patil, Honorable Minister Chandrakant Dada Patil has agreed to come. Hopefully he will come. So those are two things that change. Like I said, this is your golden opportunity to interact with people in ICER, etc. Now we are going to leave that with you. We will help you if you request Pramod or Charul. They can make some introductions, etc. But we leave it to you to take the initiative. That way we are not forcing anybody. And the last one is going to CDAC. Some of you mentioned that you would like to. So we will organize it. Just let us know what you want to do, who you would like to meet, and then work with Pramod and Charul to reorganize the talks. Right? So please work with them. I am happy to accommodate anything that suits you guys. Did you have a comment?
Past four.
Yeah.
So can the bus be arranged or we have to take it?
That we'll figure. That's a simpler thing to. If everyone goes, then bus will work at any time. But if it's just one or two, then we'll figure what's the solution. But if but if the entire class is going, then definitely the bus can be rescheduled to whatever time.
I had an interaction with Ashish yesterday. He said, Ashish,
You organize, right? Okay, I'm going to repeat this. So this is not something that I'm organizing because I love to. What I'm requesting all of you is please take responsibility for stuff that you enjoy, and we'll help you do it. Just tell us what you want to do. And you've talked about this 2-3 times, but please act on it. Okay, and we'll help you do it. Yeah. Okay, Srirang, do you want to?
Okay, so one very quick announcement. So in a couple of days, there'll be
Hello? No.
नाही हे काय
नाही
उपयोग
आता
नाही
बोल.
होत.
आता येतोय आवाज?
हॅलो हॅलो ओके. So as as Kunj has also pointed out, and I have also already emphasized that every quantum gate, as we will be doing gates today, but every quantum gate is a unitary operator acting on a state of a system. So your quantum computation is the processing of the quantum state using unitary operators. And we have already seen that only gates physically, these are gates are physical devices which have to be produced to operate, carry out that unitary operation on the state, and only a single qubit and 2 qubit gates are actually physically possible. But then we know that if you have an algorithm which asks for a unitary operation on a n qubit state, then that operation can be approximated to any required accuracy using a quantum circuit. That is, quantum circuit is a sequence of operations on different qubits out of these n qubits, and then at the end of the circuit you get exactly means with excellent approximation what you would expect as the action of the unitary operator on that n qubit state. There are two sorry. Okay, so there is one thing that I can write it here, because as you suggested, this is so suppose I have there is one, we have a single state space, and in that state space I have one orthonormal basis and there is another orthonormal basis. Is the same space, so dimension is the same, the bases are the same number of elements, and these are two orthonormal bases. Then you can go from basis A to basis B by unitary operation. So this is defined to be summation over k bk ak. So let us act on some say AL, this basis. This operates on this basis to produce this basis. So this is what can you say about this scalar product? AKAL. What can you say about this scalar product? Come on, tell me. Huh? For k equal to L, it is delta KL. So it will be delta KL. So because of orthonormality. So this will be delta KL. So okay, this delta KL. That means only when k is equal to L, k is the running index. When k is equal to L, L is a fixed thing. One state, eigenstate I am picking out, and then this operates on this Lth eigenstate in this particular basis. So the result is when k is equal to L, then only this will be 1. When k is not equal to L, it is 0 because of orthonormality. They are orthogonal. So only one term will survive. What is B L? So AL will be mapped to BL. That's it. So you can go from first, second, third, just map the whole thing. So this is unitary operator. Unitarity I will not prove, but you can assume, take it from me that it is unitary. If you want, okay. So what is U dagger? Summation over some other index I will use, say M. What is the this thing dagger of this? U dagger is AM BM. We have seen this. We have already seen that outer product operator, if I take its dagger, it just reverses. We have proved this. Okay. As I have told you, you have to you have to sit alone and go through the things. So that will help you. So now you what is U dagger U? Summation over Km, Am, Bm, Pk, Ak. What can you say about this? Scalar product delta Mk. So this will be M equal to K. So that will be M equal to K. So that will be, that is summation over K, Ak, Ak. And what can you say about this? Everything we have done. This is resolution of identity. What I mean, if you take an orthonormal basis, construct the projection operator of out of each state in the orthonormal basis and sum over them, all of them, then you get identity. This is the identity operator. So U dagger U is equal to I, so it's unitary. This is unitary. Okay. So fine. So that is one thing. Okay. We may have an occasion to use it. If something else is required, I'll prove it then and there. So okay. So we'll start with general features of quantum circuits. Okay. So this is the first thing that I want to do. Yeah. There are general features of quantum circuits which I want to list. So this is the first thing is gates that are actually used. Are exclusively single and 2 qubit. Actual circuit that you will actually implement can contain only single and 2 qubit gates. There are no other gates. But what happens sometimes is when you draw a circuit diagram for your understanding, say on a paper, you may, for example, you may have a circuit like that, I mean a gate like this. So apparently it's a 3 qubit gate. This gate involves 3 qubits and this could be a Toffoli gate. So while drawing your figure, you can draw like this, but it doesn't mean that this is a single gate and this is implemented as a single gate. You require a separate small quantum circuit to implement that gate, okay, that 3 qubit gate, and that circuit will contain only single and 2 qubit gates. That's it. Next thing is, in fact, I have mentioned it, but let me state it again. What is the general structure of a quantum circuit? Quantum circuit structure is like this, that I have n qubits, n input qubits. Okay, all of them are initially in state 0 by default, and then you have quantum wires or timelines, and then each, I mean, if you have a single qubit gate, then it it interrupts only one timeline or one quantum wire. If you have 2 qubit gate, then so you have, for example, I'll just say U, some unitary gate. Okay, so if you draw like this, then that means it is a single qubit gate which is acting on the first qubit. And if you have, say you can have a 2 qubit gate acting on, say, qubit number 3 and qubit number 4. So like this, and the execution is from left to right. So if you have, for example, if you have 2 gates acting on the same qubit or same pair of qubits, so say U1 and some U2, then U1 will be executed first. U1, which is on the left, will act first, and then the gate on the right. So if you have a gate again here, for example, say U1 and I mean say U3 and say U4. So U3 is acting on gate qubit number 3 and 4, and U4 is acting on qubit number 3. Okay. So that means they are sharing the qubits on which they are acting. Therefore, it is important the order. The order is that U3 will act first on these 2 qubits, and U4 will act later.
Top to down has equal price.
Huh?
Top to down has equal.
No, they can be yeah, I will come to that. They can be executed simultaneously, independently and simultaneously. If there are gates which are acting on different qubits, then you can implement them simultaneously and independently. So this is the thing. Then, but this is opposite to a mathematical expression. So suppose you have a gate X and gate Y acting on one qubit in a circuit like this, then gate X will act first and gate Y will act later. But suppose that I write the qubit set psi, single qubit set psi, for example, and on that I want to mathematically write this, then I have to write X first and Y later. It says, I mean, that means X is acting on Y psi first and Y is acting on psi later. So mathematical expression, the order is reversed. In the circuit, the order is strictly from left to right. Okay. Then, okay. So I have covered execution, so fine. Now the concept of measurement. See, yeah. So this is as per Kunz's suggestion. Let me write it here. Measurement is not a unitary operation, it is irreversible. If I have a superposition of states and if I make a measurement on it, then some eigenstate will pop up as a result of measurement according to the probability. How do you get the probability? You have to, that is just the mod square of the corresponding coefficient. That is the probability of that particular state coming up. And once that is done, the superposition is lost and you end up with that particular, the system in that particular eigenstate. Now I cannot reverse this process. I mean, I cannot have an operation which will act on this eigenstate and create the input superposition. This is not possible. So this is a irreversible process. So one of the lessons that I can derive from this is that when I suppose I envisage a circuit and I mindlessly put some measurement in the middle of the circuit, then what happens is circuit is processing superposition. Okay. If I put a measurement in the middle, that superposition is lost, and then we don't get the the intended last superposition that we intend to get. Okay. So मेजरमेंटचा आउटपुट एक सिंगल हे येईल नंबर येईल तर रिव्हर्सिबल इरिव्हर्सिबल आहे नाही म्हणजे तुमचं हां सुपरपोजिशन युअर इंटेन्शन इज टू process a superposition by gates, develop that superposition. For example, you have a superposition, you start with a superposition initially and you want to use gates, your circuit, such that the amplitude of one state in that superposition increases and others get suppressed. Suppose this is your aim. Okay, this is a typical aim of many circuits. Okay, so in the middle, if I put a measurement, then I will get some arbitrary eigenstate of that operator which I am measuring. Okay, so superposition is lost, and then I don't. Further, even if I have some further circuit part, that will not process that earlier superposition. That will process the eigenstate. So you will. It is quite likely that you will not get the intended result. So it's a good idea always to keep the at the end. Always try and keep the measurement at the end. And what happens is, even if logic requires a measurement in between, then there are ways of designing a circuit which will actually give you the required effects of measurements, what the logic requires. Okay, so that is possible in many cases. So this is a boon that we can do it. Of course, there are certain cases where measurements are inevitable. So what happens is, suppose now you have a case where you do want two mutually exclusive alternatives. Okay. So suppose you have, I mean, it's a binary thing. So you make a measurement, and its measurement or symbol is this, and then I will get either 0 or ket 1, but not both. It's not a superposition of 0 or 1, ket 1. I'll get either 0 or ket 1. So then what you can, I mean, what is required by the circuit, could be required by the circuit, is that if I get 0, then I go to one separate part of the circuit. If I get 1, I go to some other part. These two are mutually exclusive parts, depending on whether I am getting 0 or ket 0 or ket 1. So this is a typical case where an algorithm might require a measurement in the middle. So just to create two mutually exclusive alternatives. Okay. So when you make a measurement, you get measurement on the binary measurement, which gives you two possible outputs like ket 0, ket 1. This is the typical thing. So and then this means that you have two mutually exclusive alternatives, either this or that, not superposition. You will get either ket 0 or either ket 1 or ket 1. Okay. Measurement नंतर superposition आहे. One eigenstate, that's it. There is nothing more that is possible. Okay. So that, and then my logic requires that if I get ket 0, I do this quantum circuit. I get ket 1, I do some other quantum circuit, and these two are mutually exclusive. That, I mean, I don't want to mix this. That's it. So so this is, if this is the requirement, then a kind of measurement is, might be, you can use it. That's, but otherwise.
Crudely speaking, this is like if-else statement.
Huh?
I mean, we use if-else statement.
This is a, I mean, yeah, that's right. If you get 0, you go there, if else type. That's right. Okay, fine. So that is a classical thing. Classically, you always get mutually exclusive alternatives. You don't get any superposition anyway. So that is why these states are called classical states also. They are actually quantum states, but they are classical, behave as a classical thing. Yeah, 0 or 1. Yeah. So yeah. Who is talking? Yeah. Because otherwise, without measurement, we will not extract any information which you can see and use. You cannot see the superposition. You cannot see. I mean, in your world, you require some information extracted out of that circuit, na? That is the only way. Measurement is the only output device, only way to output the processed information.
So you do it only at the end. When you're looking for the final answer, that's it.
Yeah. You measurement. That's why measurement has to be done only at the end to get extract the information of the process state. This is the final process state. Okay, that's it. So yeah, okay. So next thing is, okay, next thing is size and depth. So let me. The size means in the circuit. In your circuit, you just count the total number of elementary means 1 qubit, 2 qubit. That is, I'll call a gate elementary if it is a 1 qubit or 2 qubit gate. Okay, so that is count all this. So that is the size, and depth has the following things. Suppose depth is total number of stages of computation. Now, how do I find out that stage, those stages? I divide them into parts such that each part contains gates acting on different qubits, so they can be independently and simultaneously executed. That is one stage. So, for example, here so this is the first stage of computation where where U1 and U2 are two gates which can be which act independently on two different qubits. So this forms a single stage of computation. Then U3 and U4 forms a second stage of computation. U3 and U4 acts on qubit number 2 and 3, while U3 acts on qubit number 1. So you can simultaneously independently execute them. And this is the third stage where U5 acts on qubit number 1 and U6 acts on qubit number 3. Okay. So this, what is the size? Size of this circuit is equal to 6, and depth is 3. So the, I mean, when you try to design a circuit, you try to design a circuit with minimum size and minimum depth, always.
And in this case, one of the outputs will be available earlier.
Which case?
Middle one, the one which measures
Yeah, no, measure नहीं कर रहे थे पूरे. I am not measuring anywhere. No measurement. Okay.
Then we can say they are stages.
That is, this is one stage of computation. This is next stage of computation. This is the third stage of computation. Okay. So this is and you have to try to design a circuit with minimum size and minimum depth. I mean, it should not. Your size should be. You should try to use as small number of gates as possible, as well as small number of stages of computation as possible. So a circuit with smaller depth is called a shallow circuit. Shallow circuit is a circuit with small number of computational stages or small depth.
आता इथे मेजरमेंटचा फ्लो कसा असेल?
मेजरमेंट नाही आहे.
नाही सगळ्यात शेवटी जेव्हा आपण करणार, फॉर एक्झाम्पल कंप्लीट सर्किट आहे.
हो, मग हे सगळं झाल्यानंतर तुम्हाला कुठली तरी टोटल 3 क्युबिटची स्टेट मिळेल साय. यू मेजर ऑन दॅट लास्ट.
Can I add a little bit on what you just said?
Yeah.
Because you said something very interesting. Like
Yeah.
you get a 3 qubit state
Yeah,
size.
yeah,
Right?
that's right.
So if you expand that out, what will it look like?
I mean, in the basis,
And what will the measurement give you?
yeah, that you can ask them. It's a 3 qubit
So-
state, na?
If you fall into one cubit,
Yeah, did you hear that?
हाँ,
So
three.
so you'll have,
हाँ.
yeah, so it could be 0, 0, 0, 0, 0, 1,
Yes,
all the way to 1.
yeah.
And then when you measure it,
You
you'll
will get
get one of those.
one of these 8 states.
And one measurement will give you one of those states.
So
That
we
is what
have 2:3 options. Out of those, we get one.
one.
Oh,
And the
that-
whole point of doing this is to manipulate the coefficients of 0, 0, 0, 0, 0.
That's it. That is it.
So that the one that represents the answer has the highest probability. Right? So it's
Yeah.
not necessarily the case that that is the one that you'll get because it's a probability.
Yeah. I mean,
If
it,
you do this multiple times,
this policy can,
Result is used for the combination of these two.
Huh?
oh no, he's just given an example.
But how we decide this?
can't.
Oh, that is where the No, I think we're going to talk about Grover's algorithm and Shor's algorithm.
I don't know, but
No,
because
we'll see the algorithm. Then you'll see how this.
no, these are actual gates that depends on what you want to do. We'll see the gates. What are the possible gates? What are the possible?
Logic we are using in programming.
Yeah, that
Right.
is that is what that. Yeah, there is one more. Yeah,
We will get this
Yes,
combination.
yes, yes.
Okay, before algorithm we cannot predict.
no, you.
No, so the
Design
gates that you're talking about, those are a function of the algorithm that you want to do.
U1, U2,
Yeah. And then depending on what your inputs are, the qubit 0, 1, 2, 3, at the output you have this superposition of these states.
In electronic circuit, we first draw a schematic diagram, then we'll write code, and then we'll get actual output.
Yeah.
So this is not schematic
No.
diagram.
So in computer science terms, we are essentially converting non-deterministic automata to deterministic vulnerability.
When we take a measurement, yes. Yeah.
So otherwise, it's a non-deterministic automata
Yes.
kind of.
Yes. I not quite NDAs, but kind of.
Yeah.
Yeah.
Because all possible states, all states are possible.
Are possible, yeah. But there's a probability
Yeah,
associated.
of course.
When you do NDA, it's not, you don't assign probabilities of it. So that's a.
See, the probability is associated with the measurement, that even if you do a measurement under identical conditions, you will get different results. This is a quantum phenomena. This part you will never get in your classical world. That is not possible. That you understand. There is one more thing that I will add to what Professor Karendekar said. See, here I am assuming that I am measuring to the computational basis. This is called a computational basis. There are infinite number of bases, and I have not orthonormal bases, and I can measure to any one of them these bases. So typically in quantum computing, you measure only to computational basis, and this is enough. We will see why this is enough, but you have to understand that it could be some other basis, some other orthonormal basis, and I could perform a measurement in principle. If you can devise a measurement apparatus for that, you can perform a measurement to that basis. But actually, it is possible that even if in that condition, suppose I want to measure to some other basis, I can use this idea, that unitary. See, suppose I have another basis and I have a computational basis, then I can use this u equal to convert this into this basis, computational basis, and measure. This is the idea. So it is always possible. You can, I mean, see, this is, I mean, measuring to different bases is just very easy to say, but it is not at all easy to do. It is quite convenient. It is quite convenient to measure to the computational basis, and this is enough because of this unitary transformation. That even if your logic requires you to perform a measurement to some other orthonormal basis, you can convert that basis into computational basis and make a measurement. We'll give an example, okay, later. Now this is one of the most important things that I'm going to say now, that I mean the evaluation of the circuit, basic tenet to evaluate a circuit is how the size of the circuit as well as its depth increases with increasing input data. That is, if I keep on increasing my input qubits, number of input qubits, how the size and depth increases with it. So if it is increasing exponentially, that is, if I have n qubits, then size becomes 2 raised to n. This is exponential increase. Then this circuit will be useful only for a very small values of n, and just as n increases, it goes beyond the possibility of building any circuit. But so this is something which is something which will guarantee the failure of your circuit. But now suppose for a given n, that is the number of input qubits, if it is proportional to n, this is the best thing that you can hope for. Then this is a linear dependence on n, and this is just as n increases, the number of gates just increase proportional to n, and then you can use that circuit for a pretty large n, pretty large input data size. Actually, in practice, what happens and what is possible and useful is some polynomial in n. So the size of the circuit goes as n square or something like that. So some polynomial in n, something like that. So that is acceptable. That generally, typically, you will find that many such circuits around, and you can do it. So yeah. Okay. So next thing is reversibility. Since all quantum gates are unitary, they are reversible. Action of U can be reversed by acting by U dagger. Okay. So always a gate has number of inputs lines and number of output lines. They match. They have to match for a reversible operation, and in fact there should be a one-to-one correspondence between them. So all this is satisfied, as you can see. And then that means the whole circuit can be reversed. That is because circuit before measurement. Forget about measurement, but
Go from right to left.
yeah, why you can, no, you can't go from right to left. But then what you can do is, suppose you get the output, you have a circuit, you have an output of it before measurement, not after measurement. Then what you can do is, to that output you apply the circuit in reverse order. It will go from left to right only, but in the reverse order, you change the order in which the gates are applied in the first circuit, taking care that each gate is reverse of the corresponding gate there, that is dagger of that, because all gates are unitary. So reverse is U dagger. So there are many gates which are also for which they are their own inverses. Okay, that means, okay, so some U equal to U dagger. They are Hermitian as well. You can have gates which are both unitary and as well as Hermitian. So in that case, you will get U square equal to I. That means you apply U first and you again apply U, you will get identity, because U is inverse of itself. So we'll immediately see this immediately. Okay. So now another thing is there is no feedback. Because many of you are used to have feedback circuits, so you can't have, it is strictly from left to right, so there is no question of reversing the order. So you cannot reverse.
Feed forward can be there.
Feed forward, that is always there. That's what is happening. So if you want a feedback, so what you want, suppose X is a gate, Y is a gate, X is on the left, Y is on the right. So this is XY, and you want to feedback the output of Y into X, then you put X again. So it's not that you are stuck somewhere, but you can always design a circuit so effectively you get the feedback, but you cannot have actual physical feedback in the circuit. That's not possible. Yeah, so if you have a measurement, then you have, suppose you have a measurement of single qubit, let's say. So you have only two options which are mutually exclusive and they are not superposed. Okay, so that is why in the circuit the output of a measurement is given by two lines, not by a single line. Just to emphasize that now there are two mutually exclusive options that are available. Okay, so that is that's what the thing is. And the last thing is the compactification of the circuit. So what you do is, I mean, suppose you have
फर्स्ट क्यूबिट होता
कुठला
त्याच्यात सर्किट तुम्ही पुसत होता
हां
त्याच्यामध्ये फर्स्ट क्यूबिटला तुम्ही U वर अप्लाय केलं
हां
त्याच्यानंतर U3
हां
त्याच्यानंतर U5
हां
त्याच्यानंतर एक आउटपुट येईल
हो
मग त्या आउटपुटला परत U5
पुन्हा
त्याच्यानंतर
त्या रिव्हर्स करायचं असेल तर, आणि जर असं असेल, if U satisfies this, then you can do this U5, U3 and U1. Other U5 dagger, it will be U5 dagger.
आणि सर ही प्रॉपर्टी आहे रिव्हर्सिबिलिटी त्याचा पर्पज काय कारण
The purpose, it's a fundamental property of quantum computation. You cannot change it. Choice नाही काय. क्वांटम कॉम्प्युटेशन कस काय क्वांटम कॉम्प्युटेशन काय करता तुम्ही, यू अप्लाय युनिटरी ऑपरेटर्स आर रिव्हर्सिबल. That is the only thing that you can do. Unitary development of a state. Quantum computation is a systematic development of an initial state to final state. How do you do it? By applying unitary operators.
म्हणजे याचा कुठे यूज होतो का
नाही याचा यूज
See one application of this in the afternoon.
हां
So keep that question in mind. When
ओके नाही हां
we talk about entropy, look sir,
हां
entropyच्या वेळेला we can talk about
या
why
मे
we want unit.
या मे बी येस. ओके, सो म्हणजे रिव्हर्स कसं होतं तुम्हाला कळलं ना.
रिव्हर्स समजतं पण रिव्हर्स होण्याची जी प्रॉपर्टी आहे त्याचा यूज कुठे होतो एक्सक्लुझिव्हली ऍप्लिकेशन मध्ये वगैरे असं
नाही रिव्हर्सिबल असणं याचा रिव्हर्सिबिलिटीचाच यूज आहे ना. यू कॅन रिव्हर्स द कॉम्प्युटेशन. दिस इज इटसेल्फ इट्स ओन यूज. in classical you cannot reverse the computation, but here you can reverse the computation. So I mean you had, I mean, many applications you can have where the reversibility is useful, but generally the fundamental, I mean, it's a fundamental thing. It's something that you cannot go beyond it, so it will be reversible always. Okay. So the last thing is, see, what, suppose I have typically n qubits, and I want to keep, say for example, a H gate on it, on all of them. Then instead of writing all this, and then you whatever state you get, you process that state further without any change in processing of different qubits. Okay, so then what you can do is you write this, and you write H tensor n, and you just put a slash like this. So that just means there are n qubits and H is applied n times. It's a compactification. That, I mean, that's not very important, but I just want to complete this. So now let's go for gates. The first observation that I want to make about gates before stating any gate is that the action of any gate, to specify the action of any gate, it is enough to specify its action on some orthonormal basis, for example, computational basis. I mean, so why? Because a general state will be a superposition of some basis states, and these operators are linear, so they will act on each term separately, and each term consists of an eigenstate. So you just define the action of that gate on all the basis states. That gives you the action of that gate on any arbitrary superposition of the basis states. Okay, and that is most general because I can choose a basis, and any state psi I can write as a linear combination or superposition of basis states for any basis. I can fix any basis and write any state of that n qubit state as a superposition of the basis states. So psi, I mean, so A1 0 plus A0 plus B1, suppose. Then U psi is equal to A U0 plus B U1. So this is the only thing that I need to know. I need to know only the how U acts on Ket 0 and Ket 1, that's all. I will get the action of U on any arbitrary state. Okay. So with this, let us start with these gates. The first gate is of course the trivial identity gate, which I will not write even. So for any n qubit state psi, write identity without any change. It doesn't change the state, identity gate. Now this is arbitrary, this applies for any number of qubits, states of any number of qubits. But now let us specialize to single qubit gates. The first gate is a sort of quantum NOT gate, which is called X gate, and this is for two possible inputs. It is, and if I apply X gate again, I will get, so that is X square equal to X is its own inverse. Okay, so yeah, that's right. So X on arbitrary state psi is X on alpha 0 plus beta 1, that is alpha X on 0, that is 1, plus beta X on 1, that is 0. So it interchanges the amplitudes or the coefficients of 1 and 0. Okay. So if I again, for example, if I again use X here, again apply X for the second time, then this is the result of the first application of X. So I apply X on this, so that will give me alpha 0 plus beta 1. So that means, that proves that X square equal to I for any state. Now the next gate is very important, is the Hadamard gate or the H gate. Yeah.
Maybe we can ask them to figure out
Yeah, that we have already done.
what already.
Yeah, so X is equal to sigma 1. Yesterday we did. That is the Pauli operator. And we saw that the matrix of X is 0, 1, 1, I mean, sorry, 1, 0. We derived this matrix. Yeah. You remember that or no? How about you? Okay. Okay. So that's it. So now H gate. So H gate is, I'll draw the figure. I'll explain it. I call it 0x and 1x. And if I apply h again, then I get back 0 and 1. So that means h square equal to 1. But then I'll prove, we will prove it. So what are these output states? So h on 0 is equal to 0x, that is equal to 1 upon square root of 2, 0, and h on 1 is equal to 1x, that is 1 upon square root of 2, 0 minus. We have already seen that these are orthonormal states. We have already seen that these, we have given the example of these two states. When I was explaining you the phase, you know, this I can write for example, this I can write as, which I have already done, but I am just reminding you, this I can write at 0 plus e raised to I pi. Okay, so this is the operation. So when I leave it for you to derive it, but h on arbitrary state psi in arbitrary single qubit state, h on that will give me alpha plus beta by root 2 0 plus alpha minus beta root 2. So the probabilities, if I make a measurement to the computational basis on h psi, h on psi. So suppose I first apply h on psi, and then I make a measurement to the computational basis. Then the corresponding probabilities are alpha plus beta square by 2, here alpha minus beta square. So let me apply h to an arbitrary state. So let us do this. So h on psi, that is, or h square on psi. Let me h square on psi, that is h on h psi. Let me do it 0, because it is enough to find the actions on basis states. So h square on 0 is h on 0, that is equal to h on so that I can write as so that will give me 1 upon square root of 2 0x plus 1x, but that is just 0. I leave it for you to calculate. What you do is you substitute the expressions here and simplify, you will get 0 there. Expressions for 0x and 1x, we have done it there. Okay, do it yourself when you have time. In the same way, if you have h square on 1, that means h is its own inverse. So actually that means h is both Hermitian as well as unitary. Similarly, x is both Hermitian as well as unitary. Okay. Okay, so what is the next gate? Next gate is the Z gate, which corresponds to the Pauli operator sigma 3. Can I erase it now here? So this is a Z gate. Z gate is the same thing as sigma 3. So you have 0x, sorry, what is this? No, no, this is something else here. Okay, 0, I want to see it on 0 and 1. That gives me 0, there is no action, it keeps 0 as it is and give you -1. So when I apply Z again, I get back the thing, that is again 0. Okay, so Z on psi, arbitrary state psi is equal to Z on A0 plus B1, that is equal to A0 minus B1. Okay. Now Z on 0x, Z on this 0x gives me 1x. I leave it for you to check it. This gives me 1x. And Z on 1x gives me 0x. So when acting on this basis, 0x, 1x, it's a basis because these are orthonormal states. So when it acts on this basis, Z acts as a not operator, because when Z acting on 0x gives me 1x, Z acting on 1x gives me 0x. Okay. The last gate that I want to see is the so-called phase gate, phase shift gate. This is called a phase shift gate. Let me do it. Phi, phi. On A0 plus B1 is equal to A0 plus e raised to I phi B1. See, if you look at this action on the basis states of phi, this phi operator, then it doesn't give you any physical effect. Why? Because if my input state is ket1, then it will multiply this ket1 by e raised to I phi, but then that is only a overall phase. E raised to, e raised to I phi ket1 and ket1, there is no physical difference because it is just a overall phase. If I take the scalar product with itself, the value is the same. We have seen this already. When we did the overall phase, we saw that overall phase has no physical impact or no physical change. Okay, so then when you act by this gate on a superposition, this becomes a relative phase. This becomes a important phase. Okay. So inverse of this is you can check that. It's very trivial to check. Check it on Ket1. Okay, So that's it. Now there is another very interesting gate which I'll take. That is square root of naught. Square root of naught gate, which is just H S H. Now S gate is by definition phi phi pi, I think. Phi equal to pi by 2. So phi that is S. So HSH. So now square root of naught square equal to HSH square, that is equal to HSH HSH. So this H into H is H square, that is I. So this will become H S square H. So A square is, so A square is Z. Let me prove it. So A square is, so yeah, I have A square. Let me, so this the matrix is 1 0 0 e raised to I pi by 2. So square you can set up this matrix for I phi also. I'll do it. So that will be R1, so R1 C1, that is 1, R1 C2, that is 0, R2 C1, that is 0, R2 C2 is raised to I pi, that is minus 1, that is equal to Z. E raised to I pi, it will come. Multiply these two matrices. So you'll get the last element in the last row is e raised to I pi by 2 into e raised to I pi by 2. That is e raised to I pi. That is minus 1. So this is A square is Z. So that means I get this is equal to H Z H, and that is equal to X, because okay, let me H Z H on 0. So that will be H Z 0x. Okay. Now Z 0x is 1x. H 1x. We already seen that Z acts as a NOT gate on 0x 1x. So Z on 0x will give you 1x. So H on 1x is equal to 1. So this is 1. So this is naught square on 0. This is on 0. This is on 0. And that is 1. So that is naught square on 0, ket 0 is ket 1. That means this square is acting as a NOT gate. When it acts on ket 0, it gives me ket 1. So that's why it is called square root of naught. So when I apply it again 2 times, I get naught. Bye. So one of the deepest implication of this is on mathematical logic. This particular observation gives rise, I am not going to talk about it, but this gives the rise of quantum logic. Why? Because in a classical logic there is no analog of square root of naught. So you have a new kind of logic here where you have square root of naught operation. Okay, so it's a new kind of logic, and there is a lot of work here basically by logicians, mathematicians and all these people, kind of people. That's not our concern. So the last gate, a very important gate, is the C0 gate. C0. So this acts on 2 qubit set 0 0. What are the states 0 0? I mean, so it is enough to find out its action on 0 0 0 1 1 0 and 1. So its gate is like this. Yeah, that part I forgot that time. Okay, I will do it. So this is the plus. Now, what is this meaning of this tensor sign between operators? So this is the definition. Let operator A act on H1 and let operator B act on H2. Then A tensor B on U tensor V. This is a this is in H1 tensor H2. A tensor B, which acts on this space H1 tensor H2 on this state which is in H1 tensor H2 is given by A tensor. I mean, I plan to say this at the beginning of the lecture, but it slipped my mind. Is okay? Is there any problem? So A is an operator which acts on H1, B operator acts on H2. Then A tensor B is an operator which acts on H1 tensor H2 in the following way, that A tensor B acting on U tensor V, Ket U tensor Ket V, which is a member of element of this H1 tensor H2, is A acting on U tensor B acting on V. It's okay? Okay. So now you understand this C0. C0 operation is this. So this acts on the qubit 1 and this I acts on qubit 2. So let me write Q1 and Q2. This acts on qubit 1 and this acts on qubit 2. This acts on qubit 2. So now suppose this acts on now 0 0. So the first term, this first operator will act on the first qubit, that this projection 0 0 acting on Ket 0 will give you Ket 0 back, and I acting on Ket 0 will give you Ket 0 back. So first term in this C0 definition of C0 gives me, doesn't change in any way, this Ket 0 0. Second term is the projector 1 1 acting on the first Ket 0 will give me 0. Okay. So that's it. So you will get, this will give me 0, a null state 0. This will give me the same state 0 0. So the whole thing gives me the same state 0 0. So this operator acting on Ket 0 0 gives me the same state 0 0. Similarly for 0 1, now this state again gives me 0 1 back, and this state again gives me a null state, because this operator, this is the projector 1 1 acting, when it acts on this, acting on 0 gives me 1 with 0. So that's it, finished. So again this 0 1 will be untouched, unchanged by this operator. Let us see what happens to 1 0. Come here. So this is 0 0, projector 0 0 acts on the first qubit which is in Ket 1. So that will give me null state. So because that's again orthogonal. Bra 0 and Ket 0 are orthogonal, so null state. This will give me, this projector acting on Ket 1 will give me again Ket 1, and tensor, x acting on 0 will give me that will give me 1 0. When it acts, C naught acts on 1 0, it gives me 1 1. It flips the second bit, second qubit. And similarly, when it acts on 1 1, again the same thing. It will not change the first thing. I mean, this will give me a null state. It has no consequence. This state, it will the action of the first operator on the first qubit doesn't change it. It is 1, and action of x on the second qubit will change it to 0. So that is 1 1 goes to 1 0. So the action is very interesting. That you have 2 qubits. The first qubit I will call control qubit. Second qubit I will call target qubit. So I can write it like this. I can draw the picture like this. So you have, these are the timelines. This is the control qubit, and this I call, this is the picture of the C naught gate. So what, suppose you have this 0, and then it could be either 0, 1 or whatever that is, that remains the same. I mean, it doesn't act on that, on the target qubit at all. If it is 0, I mean, if it is, I mean, as long as the control qubit is 0, the target qubit is unchanged. See, like this, 0 was not changed, 0 1 was not changed. So same, okay. Once the target qubit is in state gate 1, then this is flipped. Okay, so this is the action. So when the control qubit is in state gate 0, the target qubit is unchanged. Just now we saw it, we have actually computed it. Okay, when the target, I mean the control qubit is in the state gate 1, the target qubit is flipped, whatever it is. If it is 0, it becomes 1. If it is 1, it becomes 0. That's it. Now this is very interesting state, because what you do is, now suppose you put then your state is act by C naught and act by C naught. So first term, C naught is a linear operator. First term is 0 0. I mean 1 upon square root. First term is 0 0. It will remain 0 0. Second term is 0 1. So, I mean 1 0. So it will become 1 1. Remember this state? Did we do this state? While doing entanglement, we have given this example of this state is phi plus. It is a maximally entangled state. So the first state was a product state. I mean, first state I can write as 1 upon square root of 2 gate 0 plus gate 1 into gate 0. This state. This is a product state. There is no entanglement. But when I act by C naught, I get a maximally entangled state. It's not only entangled, it's maximally entangled. So this is entangling gate. C naught is an entangling gate. Okay, so yeah, let us set up the, if you want, I mean, as he has suggested, let me set up the matrix. What is the matrix? Let me just look at this operator. It's very simple. This operator. So what is the matrix for projector 0 0? Yesterday we saw. Can anybody tell me? Quickly. We have no time. 1 0 0 0. This is the matrix for 0 0. Tensor I 1 0 0 1 plus, what is the matrix for 1? I mean this projector 1 0 0 0 1. Tensor matrix for x, that is 0 1 1. So let us do this. So how do I do this? We have defined the tensor product, no? Tensor product of matrices we defined. So that is what this element 1 is to be multiplied by this matrix. So that is 1 0 0 1. 0 multiplied this matrix, so 0 0 0 0. 0 all zeros. 0 multiplied by this matrix again will give 0 0 0 0. this 0 multiplied by this plus this 0 multiplied by this matrix will 0 0 0 0 0 multiplied with this matrix 0 0 0 0. Okay, sorry. Where are we? That 0 multiplied by this matrix is this, 0 multiplied this is again this, 0 is again this, and 1 multiplied by this will be 0 1 1 0. Add these two, so you will get 1 0 0 0 0 1 0 0 0 0 0 0 0 1 and 0 0 1 0. This is the matrix for C naught. And you can check, suppose you act by this matrix on say 0 0 or I mean interesting is 1 0 or 1 1. So what is 1 0? 1 0 is I think this is 1 0 is 0 0 1 0. That is 1 0 na? Or 0 1. What? This is 1 0 and 1 1 is 0 0 0 0. So multiply. So what will be this? This will be 0. This will be 0. This will be 0 and this will be 1. That is 1 1. This operating on 0 1 will give me 1 1. I mean, if you are comfortable with matrices, you work with matrices, no problem. So this is the C naught gate. Okay. Now let us go over to some circuits. These are the yeah. There is another C1U gate. I'll just mention C1U. I will draw the figure. So it just means that if the control qubit is 0, then this U doesn't act on this qubit, this target qubit. If control qubit is 1, then U acts on the target qubit. The generalization of C naught gate, any U, any less, no problem. So this will be just X is replaced by U here. If you want the explicit operator, this is the operator. Okay. So come on. So now let me give my first example of a quantum circuit. So what is that? That is okay. Yeah, that will do a bit just a moment later. So what is the time? 11. So it's okay. I have 30 minutes. So that's fine. So okay, let's play this game. First, let us play a game. Then we'll go to some more simple circuit. The game is this. This I have taken from a video by Sohini Ghosh, I think, if I remember her right. Sohini Ghosh, who has a video which she gives this game. I have worked it out so that you just stage the game. So the game is like this. You and your friend, you have a fair coin, and you toss the coin, and if it, I mean, you toss it, say toss it alternatively, say 3 times, and 3 times n times whatever that is, and if in the final thing it turns out to be head, then whosoever has tossed for the final time wins. A very simple concocted game. It doesn't matter. So only the last throw is important, but that doesn't matter. So we want to play this game. So the corresponding नाही, चहा पण अहो 10:30ला सुरू झाला माझा, 11:30ला संपेल. हां, किती वाजले आता? हां, 11:30ला मी संपवेन. बरोबर 11:30ला सांगा मला. ओके, तुम्ही सांगा म्हणजे 11:30 वाजले की लगेच थांबतो मी. ओके, so this is the circuit. We'll analyze this circuit. Now here in this circuit, I have a measurement in the circuit. I'll justify it. So this is a control qubit, which will turn out to be either in gate 0 or gate 1. I'll explain that. The coin qubit, this is the coin qubit, which is initially in state gate 0, and this is again here H, and we have a double thing, but doesn't matter double or not. So this is my C naught, and this is again H, and this is again the measurement of the coin qubit. So by convention I say that when the coin qubit is in the state gate 0, it is head. When it is in state 1, it is tails. So this is, I'll explain this line also. So what I do is this, I initialize it to 0, this is 0. Now let us see what is happened. What happens, H acts on gate 0, so this is gate 0x. Okay. Now on this 0x is what? 1 square root of, 1 upon square root of 2, 0 plus 1. On this state, I make a measurement to the gate 0, gate 1 basis. So what is the result? Huh? The result is either gate 0 or gate 1, and this is my control qubit. Okay, this is the control qubit. On the control qubit, I first act by H, it becomes 0x. I make a measurement to this basis, so I get with half probability. Probability is 1/2 square of this. So with half probability, I get gate 0. With half probability, I get gate 1. So, it's a random thing that with 1/2 probability, my control qubit becomes gate 0 or gate 1. Yeah. So in this game, that's one thing. That whether you flip a coin or not is your prerogative. You decide whether you want to flip it or not. You can just pass it to your friend. So this is one thing. So this is the thing. Now now let us see the fate of this. This becomes 0x. Now 0x is the eigenstate of x. I told you. So let me see. X on 0x is equal to x on square root of 2, 0 plus 1. So that is equal to 1 upon square root of 2, 1 plus 0, which is the same as the original, that is 0x. That means 0x is an eigenstate of x operator, it doesn't change that state. Similarly, 1x is the eigenstate of x with eigenvalue -1. So 1x, x on 1x will give me -1x. Check it for yourself. Okay. So now this becomes 0x, x acts on it, it remains 0x. H acts on it, it becomes 0. This is one iteration. Then now your qubit state is either 0 or 1, suppose it is 1. H acts on it, it becomes 1x. I will write it on top. Now it might become 1x. 1x is this minus. Now I make a measurement to this basis. This minus sign is not going to change the probability. So again with 1/2 probability I am getting gate 0 or gate 1. So now let us see. If it is gate 0, then x will not act, and this will 0x will continue to be 0x. If this is 1, x will act on 0x, but it doesn't change 0x. So, I will get 0. So, I will get 0 always. Okay. Therefore, and you can iterate this much, up to this you can iterate any number of times. If the control qubit of your C0 gate is 0, then as if you decide not to flip coin. If it is 1, gate 1, then you decide to flip the coin. But it doesn't matter whether you flip or do not flip, you get the same result. So, the computer is going to beat you every time. No other result. Okay. But you don't have to throw your heart, because if I start with gate 1 here, I am going to win every time, because again gate 1 will be preserved in the same way in that circuit. Gate 1 will become gate 1x, which is again eigenstate of x with minus. That minus sign is overall phase, doesn't matter. When I act by h, it will again give me 1, gate 1. Is that clear to you, all of you? You people there, no problem? Okay. Now, why this is happening? This is happening because of superposition. Your gate, I mean, see, when you play this game, you will win. The probability that you will win is 1/2, and the probability that your friend will win is 1/2. Here, the probability that, I mean, it depends on the initial state, but then that will decide whether you are going to win or computer is going to win. Okay. So, I mean,
Here the probability is 1 and 0, we can definitely.
which if it is initial state is 0,
On initial state.
then the computer is going to win.
Deterministically we can
Then computer is winning. There is no question about it. Always. I mean, any number of iterations you do, it doesn't matter. If initial state is 1, then you are going to win always. Now, this result is completely non-classical. You won't get that in the classical state. Yeah. Here as if you are getting a superposition of head and tail. So, you are not going to get it when you do it with your friend actually. There is no such thing.
In some sense, what has happened is classically you get a probabilistic result.
Yeah,
And quantum mechanics is a very deterministic result.
yeah,
Exactly.
yeah, exactly opposite. Okay.
So you decide you want to win or computer
Wants to win. Okay, okay. Let us see some 1 or 2 more gates, and then we'll maybe stop. I think then by that time it will be 30. So the gate is, one gate is this, very simple, that you have 0, you have h, and this is simple, but this gives a far-reaching result, measurement to the ket 0, ket 1 basis. So this will become 0x. This will become 0, h will make it 0x, measurement will make it ket 0 or ket 1 with probability 1/2. Then what I do is, I again at the output whatever qubit I get, I put it back. This is either in ket 0 or ket 1. That
Feedback allowed.
no, physically. I'm not doing anything in the circuit. Circuit is only, I'm rerunning the circuit again and again. That doesn't stop. I mean, nothing can stop me doing that. Okay.
So whatever is the result, you fed it in by hand.
By hand.
Like
By hand. Okay. It will be now either ket 0 or ket 1. In both the cases, it will be either 0x or 1x when you act on it. When I make a measurement, again I am going to get this result with probability 1/2, even if it is 1x or 0x, doesn't matter. Again I feed it, and what I do is, first time whatever I get the result, suppose I get 0, I write 0, then I do it again, I get 0, 1, I get 1, So I get 1 1 0 0 1 1 1 0 0, and there is no it, and this is completely random. That is important. Completely random. If you do it classically, then you get pseudo random numbers. You don't get purely random numbers. So this is a fully random, no period, nothing, and uniform, because probability is 1/2.
It's not biased.
Probability is 1/2.
Galat.
So it's a completely random sequence of zeros and ones. Yes.
So why do you need to feed back the output?
Because I
Feed, not feedback.
Huh?
Feed in manually.
Huh.
Your at the output of H you have 1 upon root 2 ket 0 plus ket 1.
yeah.
So the measurement is going to give you 0 or 1 with equal flow.
Yeah.
Put another H.
So why do you need to take the output and put that?
Because I want the next digit in the random sequence.
Oh, so you want to cycle to the next.
Yeah, cycling
Okay.
physically.
Okay, fine.
Cycling. And there's no stop.
But technically, when you make a measurement, you make a zero.
Technically, what will happen is you write a program, you write a Python program, and put it in a loop, because Python is a language.
Correct.
That's it. And output you write 0 or 1 again.
Is it correct to say that technically after the measurement I put another H?
Why? I mean, I am rerunning the same circuit. That's it. That's it. That's what I'm doing.
It's in the loop.
It's in the loop.
This will generate a true random sequence.
Completely true. True random sequence. Completely. No period. Nothing will repeat. Nothing. Absolutely.
Will that depend on the first initial state?
No, it won't. You can start with ket 1, because the measurement is the same. Even if I measure on ket 0x, I am going to either ket 0 or ket 1 with probability 1/2. Even if I make a measurement on ket 1, I get ket 0 or ket 1 with probability 1/2. Doesn't matter.
Just take out. This really means that on standard classical computer with the standard random number generator, I always get a pseudo sequence.
Yeah.
But if I use this on a classical computer, I'll get a true random.
Yeah, in a hybrid program you use it. Yeah. No problem. Hybrid program.
This if I run
Huh.
on a classical system, simulator.
Simulator.
Simulator, yeah, you will
I
get
will
the
get
same.
a
Yeah,
true
yeah,
random.
simulator you will get the same. Simulator you will get the same. Yes, sure. But if you want a random number sequence,
How is the simulator deciding between at the measurement step?
I can write the mathematics of this quantum thing, and I program that mathematics on a classical system. There is no problem. Point is, this is not very intelligent thing to do, but I mean, you can do it. There is no problem. Yeah. Any
Basically, thinking of if you write the program such a way that the actual measurement will be choosing one of them.
with probability 1/2.
Yes.
Yeah.
To do that, then you have to generate a random number, right?
No, I don't have to do anything.
Yeah.
Just the output qubit I put into input again.
No, he's talking about the measurement again.
Yeah, measurement is a part of that circuit.
Give you ket 0 and ket 1.
Yeah, it will. I mean, successively when I make a measurement, it will give you either ket 0 or ket 1 with 1/2 probability.
That's what he's saying.
How to implement
Yeah.
that? That is
Yeah.
what
How to implement? I mean,
On a classical computer.
So what I was
then on a classical computer, yeah. I mean, yeah. So, what will you do? That's a good point. I mean, what will you do here? H I can. I mean, on a classical computer, I can go from here to here, but the act of measurement seems to be there. Has to be there. Eh?
But then when the number generator, because again,
Yeah, pseudo random.
So you have to classically simulate measurement, but that you cannot do.
but on
really.
hybrid it will be different.
How can you do it? No, hybrid no. Hybrid you can do. Hybrid you can do, because hybrid means what? Huh?
Or something where this
It is not connected to physical computer, quantum computer.
Yes, it is.
Physically.
Yeah. IBM has
Is it
some
a
now.
simulator
Now
or
I
is
think
it just a-
IBM has quantum computers at about 30 places all around the world. And Japan, भारतात तर नाहीये.
It's a
जपानमध्ये
hybrid then.
the program is no program is hybrid. The program is modular with some modules in classical. I mean, what your Python,
Yeah,
Fortran, or
Ethernet
whatever that
construct
is,
and all.
is completely classical, and some modules are quantum. This is hybrid.
Quantum is
So
modules
what
are
you
there
can do,
in
what
the
you can
cloud.
do is, suppose I want a genuine random number sequence in a classical my algorithm. I insert a genuine quantum module into this. That is a hybrid thing. I mean,
That is what I'm
that is what is means by hybrid. Think-
attach it to a beam splitter,
uh,
then give
that-
the feedback back
yeah.
mirrors, then that will replicate this
Beam filter will give you the edge action of edge.
action of
Action of edge. The beam edge is implemented optically by beam filter, but yeah. So
Then you need a measurement.
yeah, then you will need a measurement.
You will get 0 or 1.
Yeah. Then measurement is inevitable. That you have to- whatever way.
if it is a single photon, then it will actually make the photon go in the other direction. So that is the probability, natural probability. And which mirrors, if you can focus it back to the original beams, then it will
I don't know. I don't know.
Actually, you are making measurement physical. It's not on the classical computer.
No. If you are saying that you can do it without a measurement, then I don't think that is possible. I mean, you need a measurement of, say, for, I mean, which qubit you are using, polarization of photon or photon paths or whatever. I mean, what is that?
You can feed it back, but you won't know.
Yeah, I won't know. Yeah.
See, you want to know.
Yeah.
You can put a loop back.
That is the catch. Yeah.
But then the catch is you don't know. You can't write 0 or 1.
Yeah.
Make a measurement, you will get
Yeah,
a 0.
make a
then
measurement,
you
you
are on the
will get.
left or right of your.
Then you can.
Then you know. Then it is. That's the catch. That's the quantum catch. Can you make somehow h plus something, this becomes biased? I mean, instead of 1 over root 2, you can make it alpha and beta.
No. Classically, it is very once.
No, here.
No. Given such a sequence, I don't bother about this. What you are saying? Why? Because once I get that uniformly distributed sequence, it's a very small thing classically for a classical computer to convert it to any probability distribution. It doesn't make much problem. Okay. So if you want, I mean, you have to design kind of circuit which will give you this, but no, it is not impossible. This should be done. I mean, I'll think about it. That H will have then to be replaced by some circuit, not a you don't have gate which do that's it,
Which will mix it.
which will mix it. No,
Different than 1 over.
then yeah, you don't have that gate. A single gate will not work. You can design a circuit to do
In
it.
terms of the physical realization, we are assuming the implementation of the Hadamard gate is perfect. You're getting exactly 1 upon root 2 Kelvin.
Yeah.
Right?
That, no,
There's
that,
a
that, that,
slight-
yeah, that's a slight thing, but then
then you could get the variation on it.
no, but that is not, see, that slight deviation is random. So you don't have an estimate of what probability distribution is actually following. Okay, so that is the thing. So design a circuit. You have to first design your what kind of probability distribution over some digits you want, and then design a circuit to do it. Yeah. And this is a very fundamental problem that you have pointed out. I will not be discussing that, but there is your error correction problem. Error correction problem. So
Otherwise, the estimate will get exactly what
yeah.
you don't
Yeah.
get it. Then
But there are, I mean, error correction, you can almost get there. I mean, almost uniform. There is no, for all practical purposes, you can use it as uniform. Yes, possible. Okay, so one more circuit. The time? Akra 20. So one more circuit, small circuit. Huh? Chalo. So the circuit is this. Oh, this I didn't do. Okay. just wait for a moment, that reminds me. This is the circuit, but now this is the C naught, where your second qubit is a control qubit and first qubit is a target qubit. So there what you can do is I tensor 0 0 plus x tensor 1 1. This C dot operator corresponds to this, that then your second qubit is control qubit and the first qubit is the target qubit. Flip. So C naught can work in both. And then this, so suppose I input this, I am sorry. Then what is the action of the first C naught? Nothing. It will not change anything because your control qubit is 0, get 0. What is the action of the second C naught? So it is here it will be 1 and here it will be 1 again, because the control qubit is 1. And what is the action of the third C naught? Control qubit is 1 and this is 1, so this will be 0. So it is flipping the states. Okay, and you can generally show. I mean, I don't. I mean, I can show it if you want, but suppose I get psi. I mean, two things. So psi is equal to A0 plus B1 and phi equal to say C0 and D1. So you can make it psi here and phi here, and you can show that this circuit will actually flip it. So this will be phi here and psi here. In order for this to be useful, it must flip general state, not only the basis states. So it's algebra, you can do it. Okay, so maybe after we come back from tea, actually I want to give you how to quantum compute a Boolean function. That part we can do it next this thing. Actually I wanted to do circuits, but you already have many much gates and circuits and everything.
You have more than two. I mean, I have 1, 2, 3 qubits input. I can control with one. I can control third or fourth or fifth, or it has to be 1 and 2 adjacent.
No, but we don't gain anything. The binary sequence, random sequence, is
No,
good.
not for random sequence. This is fine. But the earlier one, that with the control bit, you can
That game,
C naught.
C naught gate.
Normally we say this and that,
Huh.
but that could be third, fourth, fifth. American.
Yeah.
That's the point.
Yeah. I mean, I not didn't say. I introduced this C1 U, and the action is if all of them are in gate 1, then it will you will right.
So technically, if all except one, there are 100, all are 0.
Anyone
I
is
can
0.
make them 1
At
with
one go.
one control.
Yeah. All control qubits must be in state 1. Then this action of U will take place. If even a single one is in state 0, finished. Because it is a product, it is taken as a product. Well, we'll close. We can continue, but I think we can close. one thing I didn't mention, that you have to show that C square is equal to R. Very easy to do. You know, A0 adjoins here, so A0 will be
Sir.
B1 0.
Yeah, okay.
Is okay, लागले. So A, that will be A00 plus B11 and it becomes an entangled state. Now adjoin the, this is the second, so this is A00 B110. Now what is the control qubit? Control qubit is the first qubit and target qubit is this is the third qubit. So this is again 0 0, so you will get this is A000 plus B, and this goes to, this is the control qubit 1 and this is the target qubit 1 0, so it will become 1 1, so it will be 1 1 1 and continue. So finally after nth qubit you will get nth, this thing you will get A000 n entries plus B. So what we are doing is we start with a single qubit state and we encode that state in an entangled state. The reason is that when you have an entangled state, we have already proved that all the information is in the non-local correlations. So if by noise, by some kind of process like decoherence process, which we are not going to say anything about, a single qubit is affected. Since the information is in the total correlation of all the qubits, that is not the information can be saved very easily. There is no problem. You can just flip the qubit and finished. Okay. So this is the way. This I mean, this is I included this circuit because this is a standard way of encoding a single qubit state into a n qubit entangled state, so as to make it insensitive to a single qubit disturbances. There are single qubit disturbances, it becomes insensitive, and generally disturbances are single qubit. Yeah. So
When you write A and B,
uh,
A, the coefficient.
it's a normalized this thing
but
position.
in practice,
uh.
A is always either 0 or 1 or half.
No, A
I
is
can put
A is any
one-
complex number.
No. In practice means when you, can I set
Uh.
a initial state?
No, it
is
could be,
equal to
no, it
0?
could, A, B could be anything with normalization condition, nothing else. No problem.
No, when I practically set,
Hmm.
I can set
See,
initiate
point,
that
no,
time
the
t equal
point,
to 0 when you
point,
set it,
point is this state,
you are always taking 0 or 1.
no, no, this state is dictated by the algorithm. This state is any state, it doesn't matter.
सरांचा प्रश्न फिजिकली आपण ती जनरली डिजिटल वर्ल्ड
मी
मध्ये 0 केव्हा 1
किंवा
करतो
1 घेतलेलं आहे ते.
काय
म्हणजे मला t is equal to 0 ला सेट
नाही,
करताना
ए अँड बी या कोएफिशिएंट विषयी बोलतोयस
या-
का?
या, coefficient
हाँ,
विषयी बोलतो.
हाँ, तो
So how do you set? I want to set the initial time state t is equal to 0,
हाँ,
which is a say point one whatever. I mean alpha and beta
हाँ,
which are neither 0 nor 1.
हाँ.
Can I do that practically?
Yeah, there is absolutely no problem. You can do that. You have to. Okay, okay, good question. So how you can do? In fact, you have your block sphere. I mean, I'm
No,
talking.
not here. No, this why I understand. What I mean is in a quantum computer,
फिजिकल कम्प्युटर
physical quantum
That's what
computer,
That's
but
what I'm
there is
telling.
no block sphere there. I have to give something.
I will tell you. Just wait. Okay. So this is my ket 0 state,
Yes.
and this is some state u. Okay. This is you want to create this. So this could be a0 plus b1. Okay. A and B are complex number, phase is included. So I need an operator which will rotate this point to this point. That operator is always available, circuits are
So I
available.
put a rotation of.
Yeah, rotation operator.
Now I start with
Ket 0.
this state, say 0 and 1 with half hour, let's say.
Mm.
Then I put a rotation operator,
Yeah,
correct?
yes.
And if I measure then I will get that with that probability if I do it many times.
No, if you rotate it, you will get a new state.
I'll get a new state.
Huh.
Now I
If
want
you
to
make a
measure.
measurement, you will get the corresponding probabilities. Nothing more. Okay, fine. Yeah. So, and in fact, you'll require this. Good that you asked it. We'll require it. Okay. So this is the last thing, I think. There are many other circuits. One more circuit, and that is you have 0, 0, 0, 0, 0, like, and you say H. So now H on 0 will give me so I can write this, it's 2. So now, and then all 0, 0, 0, then H on this 0. So if I just take 2, so I'll get H on 0 and H on 0. So that is 1 upon square root of 2, 0 plus ket 1 into 1 upon square root of 2 ket 0 plus ket 1. That is 1/2 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. That I can write as 1 upon square root of 2 raised to 2 sum over x running from 0 to 3 just x. That's it. No problem. So if I now take 3, then I'll get 1 upon square root of 2 raised to 3, again x running from 0 to 7. 0 to 7, because 8 basis states. Fourth, 1 upon square root of 2 raised to 4, 0 to 2 raised to 4, 6, 15. Understand? This is a typical input state for many algorithms. This is called uniform superposition. That's why I wanted to give you the idea that you have the uniform superposition, and typically it turns out that uniform superposition, for example, Grover's algorithm or many other algorithms, the input state is uniform superposition. Yeah, where the probability or amplitude for all the terms is the same. For example, here 1 upon square root of 2 raised to 3 is the amplitude for all of them. that way. Okay, so now let us do this. Quantum computation of a Boolean function. A Boolean function is the one which maps a string of bits to another string of bits using the logical operators. So, that is a Boolean function. We will restrict ourselves to function which maps some n bit string to only a single bit, 0 or 1. This is generally enough, because if you I mean the function which maps a m bit string to n bit string can be expressed as a ending of this kind of functions which map n bit string to 1 bit. That function can be used to express a general function. So, this is enough, this is good enough. So, now first question is, how many such functions are there? So, first question is, how many n bit strings will be there? So, if you have k bit string and you add 1 bit to it, k plus 1, then you have a k bit string and then you add either 0, say if you add 0, then you have whatever are the k bit strings, you will get those many strings with a 0 added to it, and if you add 1, you again get all the k bit strings with 1 added to it. So, they become twice. So, how many strings with 1 bit strings? There are 2 strings, 0 and 1. These are the 2 possible strings for 1 bit. So, 2 bits will be again 2 into 2, that is 4. So, 0 0 0 1 1 0 1. 3 bit string will be 2 raised to 3, 2 raised to 4, something like that. So, n bit string will be 2 raised to n. So, if you collect all such 2 raised to n bit strings and write them like this, then they form all possible inputs to this function, because it takes any n bit string to some single bit, 0 or 1. No problem? So, in order to get one function, what I have to do is I have to write its corresponding outputs below this. So, that will be, I mean, a string of zeros and ones with length 2 raised to n, because there are 2 raised to n this thing, and this defines one function. So, how many 2 power 2 power n. So, how many 2 raised to 2 power n. These many functions are possible. Okay. So, now okay. It's okay. Okay. The problem with a quantum computation of this kind of function is this, that they are not invertible, and by definition, as we were discussing about her question, that by definition, or I mean invariably quantum computation has to be reversible, has to be invertible. These functions are not invertible because their output is only single bit and their input are n bit. So, there will be so many inputs which will producing the same output. You cannot invert it. There must be one-to-one correspondence with the output. So, what you can do is you can define another function f tilde, which gives me where x is a n bit string, y single. And then you define this as f tilde of x y equal to x comma x XOR y. Okay. So this has to be invertible. So this is its own inverse. Why? Because you tell f tilde of f tilde xy is equal to f tilde x comma x or x or y, that is equal to x comma x XOR x XOR y. Now x XOR x is always 0. X XOR x is 0. So you want truth table? Do you know the truth table? X, Y. So if they are same, x XOR x may 0 XOR, there will be either 0 XOR 0 or 1 XOR 1. Both are 0. So this becomes 0 XOR y, but 0 XOR y is the same as y, because see 0, take 0, 0 XOR y is 0, 0 XOR y is 1, here 0 XOR 1 is 1, 1 XOR 0 is 1, or 0, you do not have to worry about this. I am I have 0 XOR y, so 0, I will fix my 0 initially, y's can be 0 or 1. So 0 XOR 0 is this, and 0 XOR 1 is 1, this. So this is, y is the same, okay. So this is y. So f tilde of f tilde is xy, that is f tilde is its own inverse, okay. So now I can do something with this f tilde. So what I have to do is,
Sir, in this case, x is n bit string and y is a single bit.
yeah,
So although once we do f tilde, I get that x
yeah,
XOR x. And then I put
yeah, okay. So
otherwise the operation itself cannot take this.
then this is bitwise, na?
But y is a single bit.
Oh, y is a single bit. Okay, let me. Okay, so you have. Let me check whether this is correct or no. But I think this is correct. Yeah.
X is n bit string. Yeah. X XOR y. X is n bit string. Y is a single bit. That is the interpretation we are giving. But classically XOR.
Yeah, sorry. So I was. Yeah, good. That. Sorry. Yeah. I would have realized it before afterwards, but this is the x y XOR fx. Sorry, very sorry. I mean, this is the x or y doesn't make any sense. I mean, so now this is this n. So that is y XOR fx. So that is equal to y XOR fx XOR fx. That is x comma y XOR fx XOR fx. Now this fx is a single bit, the output of f. This is a single bit. So fx XOR fx is 0. So y XOR 0 is y. So that is, sorry. So you have xy. Okay. So now we can quantumize this. How do I do it? What you need is, for a given function, okay, worst case is there are 2 raised to n inputs. So how can I accommodate them in a quantum computer. That is very easy because I just need n qubit, all possible n qubit states. N qubit states. How many of them are there? 2 raised to n. And each state is just corresponds to a string of bits. So 2 raised to n strings of bits can be accommodated in eigenstate, set of eigenstates of n qubit eigenstates. Okay, that is one thing. So n plus 1, because you need that x is n qubit and then y you need 1 qubit. So it is n plus 1 qubit. 2 raised to n plus 1 will give you, basically you will need n plus 1 qubits. So first n qubits will store x and the last qubit will store y. Okay. Now I want a UF, because that will depend on which function I am calculating. So UF xy, sorry, not ux on ket xy, that is a n plus 1 qubit eigenstate, that xy is equal to x y XOR fx. This is the quantum operator I want. And how do I calculate this value of the function? You put y equal to 0 here also, in f tilde also you can put y equal to 0. So let me do it for you. So UF x0 equal to x 0 XOR is equal to x, because 0 XOR anything is just that digit. Fx is either 0 or 1, that you should always remember. Okay. So the state of the last qubit gives you the value of fx. Okay, it will be either ket 0 or ket 1, that will give you the value. So if you measure the last qubit to the computational basis, you will get the value of fx. Okay, so like you can prove that this UF square, UF this is 0 and y plus 0 is 1. Fx is either 0 or 1. So fx XOR fx is either 0 XOR 0 or 1 XOR 1, which is 0. So that means UF square equal to I. UF is the inverse of itself. Now the beauty of this is my x could be that, I mean, could be my argument of UF could be x1y plus x2y plus xny. UF on that will be UF on xy, or x0. I mean, you want the value of the function, so y I have to put 0. So x0, x1 0 plus x2 0 plus xn 0, where x1, x2, x up to xn are the n qubit eigenstates, computational basis eigenstates, computational basis states. So n qubit, that is n digit corresponding. If you write that explicitly, then you get the string of n bits, labeling it. So that is what. So that is UF x1 plus y, x1 plus x1 0 plus UF x2 0 plus UF that is equal to x1 f x1 plus x2 f x2 plus x3 f x3 plus xn f xn. There is a single action of UF which is evaluating the function at n arguments. This is the beauty. This is the power. Of course, if you make a measurement, you will get one term out of this. But point is that your algorithm may be such that this superposition is needed to be processed further. So there it is the power. UF operator. Depending on that function, I have to find out an operator which will do this.
The last bit will have the effect of function on all possible.
Okay. So you can imagine UF to be some kind of black box in which I insert my function and this superposition, I mean superposition x1 0 plus x2 0 and function, and it will give me the value of the function at all these. That is what is happening. I mean, I am imagining it as a black box. In Greek mythology, such a black box is called oracle. So UF is called quantum oracle. UF is a popular name of UF is quantum oracle. So now let us go to some specific cases. Now suppose n is equal to 1, that is my, I mean, by the way, you have n plus 1 qubits. The last qubit contains y, and first n qubits gives me the either superposition or the single state, single n qubit computational basis state. So this is called a data register. And this is called a target register, y value, target register. Okay. So let n be equal to 1. So my data register comprises only 1 qubit, and target register of course will be 1 qubit. So n equal to 1, so n plus 1 equal to 2. So I mean, you have to, that is a 2 qubit basis states are concerned here. So now UF on 0 0 is given by 0 and second is 0 XOR F0. That is 0 XOR F0 is just F0. So that is 0 F0 then UF on 0 1 is 0 XOR, I mean 0 1 XOR F0, 1 XOR F0, that is equal to 0 1 1 XOR 0 is 1 and 1 XOR 1 is 0. So, that is just the, I will say F0 bar, that means it is just not of F0. So, if F0 is 1, then F0 bar is 0. If F0 is 0, then F0 bar is 1. That is what is happening. Suppose F0 is 0, then 1 XOR 0 will be 1. So, F0 value is negated. So, if F0 is 1, 1 XOR 1 is 0. So, again it is negated. Is it clear? And third is UF 1 0 equal to 0 0 XOR F0. What is this? Sorry, 1 0. So, this is 1 0 XOR F1 1 0. The x is 1. 1 is playing the role of x and 0 is playing the role of y. So, so 1 XOR, I mean when you act by UF, this 0 is replaced by corresponding Fx. So, that is F1 0 XOR F1. See, I will write it again. So, the same thing I am writing here, Fx, this is Fx and this is y and this is 1, is okay. So, that is equal to 1 F1, why 0 XOR F1 is F1 and F1 could be 0 or 1, 0 XOR 0 or 0 XOR 1, that is, I mean it is the same thing as 0 or 1, and UF 1 1 equal to 1 XOR F1, that is equal to 1 F1 bar. Is it right? So, these are the possible things. So, now let us take different functions. So, suppose, so f bar is not x, that is okay. The first case is Fx equal to x. Here that means F0 equal to 0, F1 equal to 1, F0 bar equal to 1 and F1 bar equal to 0. Therefore, UF 0 0 is equal to 0 0. Just check this, but use this and check it out. Then UF 0 1 equal to 0 1, UF 1 0 equal to 1 1 and UF 1 1 equal to 1 0. So, can you do you remember something from this? This action 0 0 goes to 0 0, 0 1 goes to 0 1, 1 0 goes to 1 1 and 1 1 goes to 0 1 0, that is C naught, yes. So, just that is it, I mean, so the corresponding circuit is this. this is x, this is 0, this will become x, this 0. That is the value f(x) equal to x. No? We are evaluating f(x) equal to x. So that is the answer that we will get. Now go over to f(x) equal to x bar. X bar means just not x. So this is 1, this is 0, this is 0, this is 1. So UF 0 0 equal to 0 1, UF 0 1 equal to 0 0, UF 1 0 equal to 1 0, and UF 1 1 equal to 1. So can you comment on this action? What is happening is, when the first qubit is 0, the second qubit is getting flipped. When the first qubit is 0, second qubit flips. When the first qubit is 1, nothing changes. So it is a C0 with a inverse action. That is, if the control qubit is 0, then target qubit is flipped. If the control qubit is 1, nothing happens. So how do you get that circuit? It's very simple. The circuit is, yeah, I can put it this way. X gate. So I have X is a single qubit state. X gate will give me negate it. So if it is 0, it will become 1, and nothing will 1, it will change, and again it will become 0. If it is 1, it will become 0, nothing will change, and again it will become 1. So this inverse operation is many times is denoted by this. That is, instead of a field spot, you have a circle for the control bit. That means it is like this. It is I mean the target qubit is changed when control qubit is 0. Ulti action. So if you want to show that, then this is a compact convention. When you have open 0, that means it is inverted. Otherwise, you can write this complete circuit. No problem. Huh?
Zero ni control.
Zero ni control. Maybe zero.
Zero.
Huh? Yeah, that's right. Okay. So I give you this exercise, that now you find out the circuit and all action for f(x) equal to 1. So f0 is 1, f1 is also 1. You find out. Okay. Find out the circuit also. The same way we did. The way we did. Now we go over to a very important circuit, which is called phase kickback. Phase kickback. Very useful and is being used everywhere. I'll draw the circuit and then we'll see this. I'll explain this. I'll explain this. So this is the control qubit here is control U, and control qubit is initialized to 0, then H, okay, and then this acts, but before that the target qubit is rotated, as Professor Kanere pointed out, and I told him that how to go to or by rotation for to any desired state. Okay, so U is the desired state. What is the criterion for U? U has to be the eigenstate of this capital U. So I start with Ket 0 and using a proper rotation operator, I go to an eigenstate of capital U. Okay. So now what is the action? Let us see the action. I know that since this is an eigenstate, we have already proved that its eigenvalue is a purely imaginary. We have proved it. Okay. Okay. So now my okay. So my this becomes 0x. So input to my C1U, this C1, this is C1U, okay, is 1 upon square root of 2 Ket 0 U plus e raised to I phi 1 Ket 1 U. Do you agree with this? See, if you want more with more steps, this is the thing. So what happens is this is your square root of 1 of 1 upon square root of 2 Ket 0 plus Ket 1 is here. So when for Ket 0 nothing will happen, so you will have Ket 0 here, and for Ket 1 it will be multiplied by e raised to I phi, because it acts on U. U acts, this capital U acts on U to give you e raised to I phi into U. So you will get this into U. So that's why I just wrote it inside. So this is your state after application of U, application of C1U. Okay. So that I can write like this anyway. So what is happening is this e raised to I phi factor is generated due to the action of this U on U, but that goes and sits into the state of the control qubit. That is why it is called phase kickback. This is a phase factor getting generated by the action of capital U on small u, that is this Ket. Because why? Because this Ket U is the eigenstate of this U, and this is the thing that when U acts on its eigenstate, the eigenstate gets multiplied by e raised to I phi. So you can start with this 0x is your here. So square root of 1 upon square root of 2 into bracket Ket 0 plus Ket 1, and this is U. This is the input state. This acts on this. So Ket 0 nothing will happen. So you will get Ket 0 into Ket U, and then Ket 1 U will be applied to Ket U. So that will give me e raised to I phi Ket U. So that is precisely. See, 0x you write explicitly 1 upon square root of 2 Ket 0 plus Ket 1 and act by this. So what is the input state for this? What is the state before application of this gate? It is 1 upon square root of 2 Ket 0 plus Ket 1. This is the input state or you can write as K0 u plus K1 u. The first term, what is the action of this on this first term? Nothing will happen. What is the action here? U will act on this u. Huh? What is the result? E raised to I5. So this is so C naught or U naught, whatever it is. C1 U. Huh? Okay. Now this will rotate, not physically. This is a rotation operator on the block sphere.
Because I5 is just changing the phase.
Yeah, it changes the phase, it multiplies the phase. So that is action of C1U will give me 1 upon square root of 2 0 u plus e raised to I phi 1 u, which is equal to 1 upon square root of 2 0 plus e raised to I phi 1 u on the first qubit. Although the process of generation is the action of capital U on small u.
It is mathematically clear. Physically also this happens.
Yeah, physically. What do you mean? This is all physical. This is all physical. Okay. So you are getting this state. This is the state of the control qubit. The phase generated at the target qubit is transferred to control qubit. It's phase kickback. It is. It's not a kickback. I mean, sorry. Okay. So now suppose the qubit n qubit data register is in n qubit computational basis state X, dictated by the n bit string on which you want to evaluate f, and the target register is in 1x. This is the state of the target register. It is a single qubit, and your data register is n qubit register whose state is x, is a computational basis state, some computational basis state. The operator UF computing a function f. So you have to, function that you want to compute is f zero 1 raised to n to 0 1. So this is a single bit and this is a n, means the n bit string. So this acts on x 1x, that is equal to 1 upon square root of 2 x, I am sorry, x 0 minus x 1. So let me write it explicitly. UF on x 1x is equal to 1 upon square root of 2. Just follow it. I mean, this is all. That is equal to 1 upon square root of 2 x 0 XOR fx minus x 1 XOR fx. that is equal to 1 upon square root of 2 x f x, because 0x for f x is just f x, minus x 1 f for f x is f x bar. So, this is what I get. Now, if f x is equal to 0, then you get x 0 here and x 1 here. Okay. So, I take x out, I mean, no, let me write it. So, for f x equal to 0, I will write it, f x equal to 0, you have f x is 0 here. So, I will get this action of u f will be x 0 minus x f x bar, that is 1. I take x out, 0 minus 1. This is 1x, so that is equal to 1x 8x. If f x equal to 1, then this is 1, this is 0. So, this will be minus 1 into this x. So, that is minus 1x x. Have you, is it clear? No. Why? See, f x equal to 0, start at least f x equal to 0, is it clear or no? F x equal to 0. So, this will be 0, this will be 1. So, that I have written here. I mean, now I have written that f x equal to 1. So, f x equal to 0. So, this will be 1 upon square root of 2, x I take out. So, 0 minus 1, 0 get 0 minus get 1. So, this is 1x. So, 1x into x. So, this is for 0, x equal to f x equal to 0. If f x equal to 1, if f x equal to 1, then this will be 1 and this will be 0. Okay. So, I take x out, I will get 1 minus 0. So, I will get minus, if I take minus sign out, I will again 0 minus 1, get 0 minus get 1. So, this is minus 1x. Okay. This I can write as minus 1 raised to f x as a phase factor. Into bracket x 1x. If f x equal to 0, minus 1 raised to 0 is 1 and then it will be x into 1x. If f x equal to 1, minus 1 raised to 1 is minus 1 and it will be minus as it is. So, now let us do this analysis on a superposition, that will be more interesting. Huh? Why not? I want to consider this. No, but why not? You, if you want, you consider 0x. Then that you will understand in a bit. Okay. But you cannot challenge me. I mean that that is the point. So let us. Okay. So my now is alpha x1 plus beta x2. This is the state of the data register superposed. X1 is some basis state of the n qubit computational basis. This is another element, another eigenstate of n qubit computational base member, and this is the superposition. And again, this is my the target register again in this state. So this is the target register is 1x. So UF on alpha x1 1x plus UF on beta x2 1x. I don't need this. So UF on this product. This is the state on which I am acting by UF. So that is alpha UF on this. So 1x I take inside. So this is the thing. So this is, I will go up. Okay. So that is equal to what? Alpha x1, and now this UF on this is alpha kate x1 into minus 1 raised to fx1, that is alpha kate x1 to minus 1 raised to fx1 plus beta x2 minus 1 raised to fx2 1x. Okay. Now what I will do is I will multiply this by the overall phase minus 1 raised to fx1. So when I multiply this, it will become alpha x1 kate x1 minus 1 raised to fx1 XOR fx1 plus beta kate x2 minus 1 raised to fx1 XOR fx2. And this into 1x, I think. Yeah, this into 1x. Okay. I have multiplied by e raised to minus 1 raised to fx, both terms. So it's a overall phase. It doesn't change anything. Only the form is changed. Overall phase is not physical. It's not going to change anything actually. But mathematically, you can always do it. There is no problem because it is convenient to me. What can you say about fx1 XOR fx1? 0. So minus 1 raised to 0. So that goes. And what can you? So this will remain. So I will get alpha x1 plus beta x2 into minus 1 raised to fx1 XOR fx2 and whole thing into 1x. Now there are two cases. One is if fx1 equal to fx2, then what will happen? What can you say about this? Again 0. So this is 0. So what is the result? If fx1 is equal to fx2, the result is alpha kate x1 plus, because minus 1, this is 0, so this is minus 1. So beta kate x2 1x. Because this is 0 if fx1 equal to fx2, and therefore minus 1 raised to 0 is plus 1, and therefore I get this. if fx1 is not equal to fx2, then it is 1. So, that is, so in that case fx1 not equal to fx2, then it is alpha ket x1 minus beta ket x2 1x. So, now if I measure my data register, so depending on this condition whether fx1 is equal to fx2, the data register will be in this state alpha ket x1 plus beta ket x2. Yeah. Yes.
Answer is 1, minus 1 is to 1.
Oh, minus 1 is to 1. Yeah.
So minus 1 multiply with that bracket, so alpha.
So कोण बोलते मला वाटलं तुम्ही बोलताय ते तुम्ही स्वतः करून बघा म्हणजे fx1 इज नॉट इक्वल टू fx2 असा जेव्हा असेल -1 रेस टू fx2 XOR fx1 XOR fx2, if fx1 is not equal to fx2, then fx1 XOR fx2 is 1. So, -1 raised to 1. So, that is -1 will come there. So,
That equation minus alpha is
huh? Minus beta, though I have written in the first place it is fx1 XOR fx1. So, it is always 0.
No, not with beta. No, not with that.
I do not understand what you are saying. Okay. So, this is the thing. Okay. Okay. Just a moment. So, now in order to find out, make a distinction between these two cases, okay, these two must form a basis, orthonormal basis. Then I can make a measurement to this basis and then I will find out which is the state, whether the first state is, I mean I will get one of the two states. Okay. So, okay, so what is happening here now? Let me check. Okay, so yeah, now my result is this: if the state of the system is this state, then fx1 is equal to fx2. If the state of the system is this state, then fx1 is not equal to fx2. Now, the system is in one of these two states, it is not in a superposition or anything. So, if I make a measure, if these two states are orthogonal, then these two states form a basis and I can measure to that basis. If I do that, then if the system is in this state will come out, because it is an eigenstate of that operator which I am measuring. If the system is in this state will come out, and I will know whether fx1 is equal to fx2 or fx is not equal to fx2. For this they have to be orthonormal. The condition for orthonormality is mod alpha equal to mod beta. I can prove it, but let us postpone it for the moment. If mod alpha equal to mod beta, then these two will be orthogonal, and if these are orthogonal, I can make a measurement to this basis. And since the system is either in this state or in that state, is one of the eigenstates of that. Yeah, we can identify, and then we know whether fx1 is equal to fx2 or fx is not equal to fx2. So, global information on we don't bother about the values of fx1 and fx2. This is a global information, whether they are equal or they are not equal. The values could be anything. Values could be both 0. If they are equal, they could be equal when both are 0. They could be equal when both are 1. But I do not bother.
So, in a way we do not care about function fx.
No, I want a global information on f, whether f is giving me values of f at x1 and x2 are equal or they are not equal.
Yeah, but what that f is, I do not care. What exactly that f is, I do not care.
No, f I know, I mean, f is to be known, so that UF has to be known, na? UF is has to, you have to construct UF, but then okay. So what is happening? What is happening? Let me see. Let us see what is happening. So what is the action of UF? No. So okay. So we don't have to know F. I agree. We don't have to know F. F could be, I mean, F possible functions, 2 raised to 2 raised to 1 functions. It could be any such function. And then we don't know F, but because why this is possible? Because UF has the same form. It has the same form. So this analysis goes through completely for any F. Okay. So F is fixed, but it is not known to me. It is not known. Yeah, it is not known. So I have a global information on F by this, whether fx is fx1 is equal to fx2 or not. Okay. And most important thing is, I have used UF only once. Suppose classically you want to do it, you will have to evaluate f at x1 and x2 both. So two evaluations are required, and then you will know. I mean, you can see whether it's equal or not. That's trivial. I mean, that is not very important also, because once you know all the values of f, then there is nothing that is interesting there. But without knowing the values of f, you know here that f has the same value. This is the root of Deutsch algorithm.
This is the
Deutsch algorithm. We will come there just in a moment. I am starting with this. So okay. So these two observations I made, that this is a global information about f. Okay, and this is a global information about f. This is the first point, and secondly, you have to apply the evaluation is only once. That is, you apply UF only once. You don't apply UF twice. That is, you are not evaluating f twice. You are evaluating f once. So this is the quantum advantage. Okay. So this is a special case. Deutsch algorithm is a special case of what we did. Let us see. See, I want to, I mean, so these are the 4 possible functions of a single qubit string. Okay. So this f0 and f3 have the same outputs. So these are called constant functions. f0 and f3 are constant functions, while f1 and f2 are balanced, because as many number of zeros as many number of ones. That is the state. That is the definition of a balanced function. But these are balanced. There are only 2 entries. One is 0, the other is 1. So f1, f2 are balanced functions, and f0 and f3 are constant functions. They are the same output. And we want to know whether the given function is constant or balanced. That is it. So exactly the same thing. So what you do is, here, I mean, you have now x1, this your data register has only 1 qubit. Okay. So you have alpha x1 plus or minus beta x2 into 1x. This is the thing that we will get. So, if it is plus, then the output, there are two outputs. If this is plus, then you will get okay. So, we will put both 1 upon square root of 2. Okay, and this is 0 and this is 1. Why? Because there is only 1 qubit. So, that becomes so if it is plus, then it is 1x. So, that is your output is 1x 1x. If it is minus, then it is, I mean, if it is plus, it is 0x, sorry. If this sign is plus, then you get 1 upon square root of 2 ket 0 plus ket 1, that is 0x, and if this is minus, then it is 1x. So, that is 1x 1x. So, you can just leave it out. Your control qubit is either 0x or 1x. Okay. So, if your values of f are equal, that is if it is either f0 or f3, then this will be plus. If the values are unequal, then this will be minus. So, what I can now do is I can put an h operator here. So, I will get, if it is 0x, I will get 0, if it is 1x, I will get 1, and then I measure to 0 1. So, the output is 0, that means function is constant. If output is 1, the function is balanced. Circuit, you want to draw the circuit? It is here. This is the circuit. This is 1x. This algorithm is of historic importance because it was first devised by actually a very genius person, David Deutsch, giving the first demonstration that of quantum advantage, that it's worth thinking of quantum computation. First algorithm by David Deutsch, who proved that it's I mean, quantum computation could be beneficial. 1985 paper. Okay. So, what else do you want me to do? I have also told you about quantum parallelism, that is UF acting on the superposition will give you, it can evaluate the values of the function at so many places, at so many arguments. Take superposition and act by UF, you will get the value of fx at so many values x1, x2, x3, x4, the bit strings defined by the data register. It's in superposition of the corresponding. So that is the quantum oracle. You the black box, you plug in f and you plug in that superposition, you will get the function evaluated at so many arguments at the same time.
So sir, this is being used to get the global information about the functions. That
About the function, about the
either
function.
is
Yeah,
it
yeah,
F0 or
yeah,
F3 or F1.
So yeah. So it will not pinpoint particular function,
Yeah.
but it will tell you whether it is f0 or f3 or f1 and f2.
So that the zero, the ket0 and ket1 actually signifies that.
See, if it is ket0, then it is constant. That is, it is f0 or f3. If it is ket1 comes out, then it is.
Actually, this constant, I think you had taken just as illustration. What you
No,
actually
no, no.
take
These
was-
are the, see, for if it is 1 qubit, then it is 2 raised to 2 raised to 1. Okay. 2 raised to n, na? The total number of functions, 2 raised to 2 raised to 1. That means 4 functions possible. So these are the 4 functions. Na? Four functions per bit. You can't have more than this. So what is the time? I mean, lunchtime. Okay. Nobody is telling me the exact time. Lunchtime. Okay.
One last question.
Huh?
Here in this case, because that n was equal to 1, that's why you got 4 functions.
Yes.
Let's say I had n equal to 2,
Yeah,
then
yeah.
I would have got 2 power 4, that is 16 functions.
16 functions.
Now, in that case, the property of the functions which are equal,
No,
at
that
level, they need
not
be constant.
no. Out of these 16 functions, you may have functions which are neither constant nor balanced.
Balanced
Yeah,
functions.
yeah.
And
So-
even if they are, even if the, let's say some function f1 is
Hmm.
equal to f2 for all values, that doesn't mean that.
No, that will never happen. Then it's the same function,
No,
no?
it's not same. But what I mean is
Constant.
Constant function.
constant function. Okay. So output is still 1 bit.
There are only 2 constant functions, even if you have n equal to
Yeah,
2.
the output is still 1 bit.
Output is 1 bit.
1 bit.
Function.
Yes, yes, fine, fine.
You are considering functions which map n bits to 1 bit.
ठीक.
Always.
And if you're in the classical space,
Yeah.
if you wanted to solve this,
Then you have to evaluate.
comparison could be
Yeah.
how many?
Yeah.
NC2.
Yeah,
No.
or in this case, two comparisons.
Yeah.
Yeah.
Whereas in the
2
quantum case,
is 1.
There is one measure. Yes, actually, we are getting logarithmic array.
yeah, so really speaking, this is not a problem that people really care about.
No, this is not. This is a demonstration. Demonstration. This is
It
demonstration.
explains that principle that you go from exponential to linear.
This was extremely important in 1985, not so much now. The first demonstration of quantum advantage. Huh? Yeah, depth is, you can see this. I mean, no. See, this one is first thing. This one alone is the second stage, and this is the third stage, and this is the fourth stage. Fourth stage. How?
So it's based on the algorithm you are putting.
Yeah.
But proving optimality might be difficult.
Which kind of optimal?
Yeah, what do you mean by optimality?
Yeah, the sir said that size and depth should be minimized. So
Yeah. I mean, but that depends on what you want to do, what is your algorithm and all that. I mean, there is no general method to minimize arbitrary circuits or something. That's not possible.
I haven't thought about it, but there's probably some amount of, the traditional trade-off between depth and number of.
Yeah, similar, yeah, that's right. Yeah, that's right.
yeah, typical parallelism.
Shallow then? Is it okay? Yeah. Thank you. So I have one lecture left on Wednesday.
That's information.
That, what I will do is some small algorithms I'll take. You want a general information, this thing? I can
We'll
do
talk
that.
about it offline. We'll look at the contents.
all right? Okay. Now, the question that we can get into is what we talked about is transmitting a signal through a channel, right? So what we can talk about is what is this signal, what does it represent, and how do we quantify it? Okay. Actually, I want to do this. Let's talk about some of these questions, right? Okay. So if I am transmitting some content, to be or not to be, that is a question, and then a whole bunch of, so I have two possible messages that I'm transmitting in a channel, right? So which one, just intuitively, like don't apply any technical definitions out here, but which one has more information than the other? The first one? The second one? So you're speaking like a true electronics or electrical engineer.
Computer science brother, but
Okay, but so what do the rest of you all think? How many think that there is more information in the first string versus a second? Okay, I shouldn't have said what I said. How many people think the second? How many people think the second has more information? A lot more. Why?
patterns basically. There are patterns in the first string.
Yes,
And there is no pattern in the
in the second string,
Yeah.
and therefore
The information content in the first string is less.
less, right? So if you were to see just this much, to be or not to be, right? Can you predict what the next word is going to be? Yes? I mean, assuming you're familiar with Shakespeare, right? Or let's say I say Jana Gana Mana, can you predict what the next word is going to be? Right? So there is less surprise. So if you get the next word, it is what you expect, right? So the amount of information out here, so out here if I stop out here after the 1, can you predict what the next letter is going to be? You can? In this string? No, out here, so like in the second string, right? You can't, yeah, you can't tell what the next, yeah, sorry, I meant, yeah. So in that sense, right, the first string, while we can interpret it, it has less information than the second string, right? So there is this difference between kind of the semantics, the meaning of what we are transmitting versus the information content. And this is actually the genius of Shannon, because he was able to go in and tease out these two concepts and then quantify what information meant. And that's what we're going to look at, right? So, okay, this last question is very interesting. How would you define information, given what we just said, right? That in a sentence where I can predict, or in a string, when I can predict what the next word or symbol or letter or character is going to be, right? If I can predict that, we say that there is less information. If I cannot predict it, there is more information. How would you formulate that? How would you try to capture that definition of information? Yeah, other than you or people who know the answer. So just intuitively, like not a formula or anything, just intuitively, how would you think about it? Oh, very nice, right? So did you guys hear what he said? The minimum set of symbols required to convey the information, right? So how many bits maybe do we need to encode this versus how many do we need to encode this? Yeah, so this happens twice. So we can encode it using a single symbol, and then we don't need all of the bits for that, right? Yeah, we are going to go towards Shannon entropy, but
I didn't say anything.
but yeah,
Shannon, so I came.
yeah.
But I think one step earlier we can just say that the information content is inversely proportional to the probability.
Probability, exactly, right? So if the next word is highly probable, then the information content is less, right? They are inversely related to each other, right? So thank you. That's exactly what we. Here's one more thing, right? Suppose I have two different facts about something. Let's not worry about these strings, right? If I combine those two, so I have a certain amount of information because of the first fact, a certain amount of information because of the second fact. How do I combine those two? How much has my knowledge increased because I have both facts with me?
Then you have to figure out frequency of
No, let's keep it simple. So let's say,
probability of this event happening versus that.
yeah, okay, so hang on. So two independent events, right? Where I was going with this is the information that I have is additive, right? I have fact 1, I have fact 2. Now I know both fact 1 and fact 2, so I can add them up, right? My knowledge has gone up by acquiring both of those facts, right? Probability, if I have the probability of one event and the probability of another event, what is their combined probability?
PA plus PB.
Is it PA, so PA plus PB?
Minus probability of A intersection. PA of A intersection.
Oh my God, you guys are going very well. Actually, so first of all, it's not even PA plus PB. If they are independent events,
Then
it is the product of probabilities, right? The probability of two heads is, yeah, half into half, right? So at one level, we started off by saying that information is inversely proportional to probability, right? And then if we say that, okay, let's look at a combination of events that is increasing the information that I have, intuitively I will add up the, each one of them, the information that is giving me is adding up. But then we also said that, hey, this is related to the probabilities. Probabilities are combined by multiplication. How do we reconcile these two? Sorry? So I want to end up in a place where I'm adding something, but I have a product. How do I convert a product into an addition?
Okay.
You take the logs, right? So if I want to say that fact 1 is giving me a certain amount of information that's proportional to log of the probability. The second one is a log of its probability. If I add those two up, it's the same as adding up the information. So we are kind of getting these two together, what we know about information, and we're relating it with probability, right? Log has another very nice property that we can use. We just said that the information content is inversely proportional to the probability, right? Probability goes down, information goes up, right? What can I do with logs that captures that?
Scale it up. Scale it down.
But that will still, it won't convert the, it will still be inversely proportional.
Yeah, you can convert division by subtraction.
Yes, exactly, right? So what we'll be doing is, we'll be calculating the negative log of the probability, and that is what we will use as a definition of information content, right? This is great. I thought I would have to write all of this down, but it's nice to, yeah. True.
Definition of randomness.
Yeah.
If it is random, if there is no other way for any computer program to
To actually reading it, yeah.
Cannot be generated by any.
Right.
That is maximum. I mean, that is the definition of random. Kolmogorov.
Right, or maximum entropy. Yeah. Okay, so let's quickly go through these. What was Shannon's core paradigm shift regarding the definition of information? That actually works in this case as well, right? He separated the semantic meaning of a message, because when we read a sentence and we say to be or not to be, that is a jana gana mana, we understand it and we assume that has more information. That is a semantic meaning of a message, right? But from an engineering perspective, it's the opposite, right? If you can't predict it, then it has more information, right? Everyone okay with that? Yeah?
Permission to transmit.
Transmit, or even, if you're reading something, like sir said, the only way of figuring out what the next symbol is to actually read it. There's no way of predicting what it's going to be, right? But yeah, in this case, we're talking about transmission. Yeah.
In that question,
Yeah.
that third one is pretty okay.
So it is true, but it is not what Shannon was. The question was very specifically, what was his paradigm shift?
Yeah, of course,
So-
he didn't do that.
Yeah.
The same principle is used in compression.
Well, yeah. So
It did not discuss.
yeah, and in fact, is there a way to perfectly compress random data strings?
You can know the lower limit.
Yes,
but
exactly.
You may not know the way.
Yeah. But anyway, Shannon didn't do that. Okay, why does an analog signal inevitably degrade over very long distances? Again, longest answer. Right? Okay. How does digital thresholding solve the problem of cumulative noise? Let's see, what is the longest answer? It is actually, oh God. Okay. This is something we're going to talk about, so don't worry about this right now. Yeah, let's not talk about this right now. I'll talk about what a bit is. Yeah, if something is 100% predictable, right? If the sun is going to rise tomorrow, how much information do you gain if the sun actually rises tomorrow? Zero, right? Okay, which require more bits to transmit perfectly without loss? An image of black pixels, a repeating sequence of ones and zeros, text file with hello written 10,000 times, and an encrypted file with last one, right? So that has the most amount of information. Okay. So I'll just show you what I thought I would have to write out, but basically we have a message, we can calculate the probability of a symbol, we can define the information content in the message, and you know, that's kind of related to how much surprise there is. If you have Jana Gana Mana and I don't know, the next word is Jaya He, you are going to be very surprised because that's not what we were expecting. We have two messages, information and probability are inversely correlated, right? So now, what we already not discovered, what we already talked about is that this information, क्या हो गया? Okay. So this information, what we already said, is basically going to be log of the probability of x and the negative log of that, right? So now we go from a relatively abstract concept of information surprise to a mathematically precise definition of what we mean by information, right? So this is fine if you're looking at just one symbol or one word, right? What if we have a whole sequence, we have a whole sentence, or we have an entire string? How would we capture the notion of information out there? We would look at the expected value of that particular string, right? And from statistics, what is the definition of expected value? The weighted average, right, of all the outcomes weighted by what? So it's probability times the information, right? So this is going to be probability of x into log of probability of x, and we sum it over all x, and that's of course negative log of this, right? So expected value of any string or any sentence can be defined as the what did I just say? So this value, right, is it's called Shannon's entropy, or it's the entropy of a signal, and it's nothing but the expected value of that particular string, all right? And now you can see this in action, right? So if I have a fair coin toss, right, what is the probability of a head or a tail? 1 by 2. So if I were to calculate the entropy for that, I have two outcomes. each of them have possibility 1 by 2. So this calculation becomes 1 by 2 log 1 by 2 plus 1 by 2 log 1 by 2 and negative of this whole thing, right. So that's log half, which is log 2 or negative of log 2, the negatives cancel out. Log of 2 to the base 2 is 1, right. This is the definition of a bit in information theory. So in digital logic or regular computer science, we just think of bits as binary digits 0 or 1, but now it is this value, right. It is, you could think of it as the number of questions I have to ask in order to get the answer. So in a coin toss, I have to ask one question to find out whether the outcome is a head or a tail. Okay. Let's do another experiment. Suppose I have a very biased coin, right, and it has, let's say, let's take a power of 2. So let's say it's, you know, the probability of head is 1/8 and the probability of tails is 7/8, right. I can do the same calculation or similar calculation. I'll be doing, hang on, I'm running out of space. So I'll be doing 1/2 log 1 by 8 plus 1/2 log 7 by 8. Or let's not do divided by 8. I can do log of 0.08 plus half log, no, but that's 0.92. I'm trying to avoid, so, you know, if it's a power of 2, I can take the log to the base 2, but 0.92, I don't know how to do. But anyway, the point is, right, this is going to give me a number that is much less, sorry, this won't be half. Yeah, sorry. Yeah, 0.08 into this plus 0.92 into this, right. So the point is, it will be a number that is, yeah, and there's a negative sign behind all of this, right. This will be a number that is much less than 1, right, and see if it makes intuitive sense, because what we are saying is, if I have a 8% chance of a head and a 92% chance of tail, right, I don't need to ask one question, I need to ask a fraction of a question, which doesn't make sense. But then you could say, okay, suppose I have a string of 100 bits that I'm transmitting, right? How many bits do I need? How many digital bits, computer science bits do I need in order to encode that particular string? The answer is going to be much less than 100, right? In the first case, for a balanced coin, right, I need 100 bits. Because for every coin toss, I need to say, is this a head or a tail, 0 or a 1. So I need 100 bits to transmit the outcome of 100 coin tosses. But for this, I need a lot lower, right. So information bit captures all of this stuff, right. It captures the amount of uncertainty or the probability. It captures, it answers the question, how many, it answers the question. It says how many questions do I need to ask in order to determine what the output is, right. And in a sense, if you relate back to what happened before lunch, right, when we had the balanced versus unbalanced functions, right. In the classical sense, you had to ask 2 questions in order to get the answer. For quantum, you have to ask only 1 question, right. So, but that's a separate thing, but an example of asking the question. Why is this called Shannon's entropy? I found this quote that was pretty interesting. So he says, Shannon didn't know what to call his new formula, so he asked von Neumann, who said, call it entropy for 2 reasons. In the first place, your math has been used in statistical mechanics under that name. So we're going to look at the thermodynamics definition of entropy, and you'll see it's very similar to that. So it already has a name. In the second place, and more importantly, nobody knows what entropy really is. Well, so in a debate, you'll always have the advantage, which ties into what Kunj showed us right at the beginning. With quantum mechanics, you know, nobody knows what it is, so we are all in the same state of ignorance. Okay, so let me go back to this part. Okay, so this kind of captures everything that we've said. You know, the information is negative log to the base 2 of px. This is the definition of entropy, and this is the thermodynamic definition of entropy, right? Kb is Boltzmann's constant, right? And S is the amount of entropy in a system, right? And the second law of thermodynamics basically says the amount of entropy or disorder in a system always increases, right? So now that let's think about how these two guys are related. You see how close they are. Px log to the base 2, this is pi natural log of pi. So we call it a bit because that's log base 2, right? We could have used ln out there and we call it nat or something like that, right? The base of the log really doesn't matter. So they are equivalent. What you're missing is the Boltzmann's constant, right? And I'm with apologies to the pure physicists in the audience. One thing I really enjoy is how we kind of look at systems and we see they are similar, and therefore we use insights of one in the other. So I found that in, for example, when we are looking at the wave versus particle nature of light, right? I find a lot of similarities in that. So for example, an electron, right? Can it behave like a wave instead of a particle? Sure. Or a photon, does it have momentum? Sure, right? I mean, I'm sure there are proper physical theories behind it. But from my perspective, I just look at the two of them and say, sure, we can apply one lens to the other. So we're going to do something very similar out here. We've come to a formulation of what we're calling entropy because the formula looks the same. But we're actually going to use that fact that the formula look the same to do a little bit more, to get a little bit more insight into what's happening. Okay, yeah.
We can argue that even Shannon was trying to calculate the amount of randomness in the system.
Yes, and so from that sense, it is exactly like entropy, because if you have, maximum uncertainty, your Shannon entropy increases, which is what it should be, right? Okay, this is just a little bit of a cartoon where, when you have a perfectly fair coin, 0, 1, your entropy is maximum, it's 1 bit. And if you change this in either direction, of course it's going to be symmetrical, your entropy goes down, right? So it's just a little bit of a cartoon out here. Let's do this.
Perfect thing has a highest entropy.
Well, the most balanced thing has highest entropy, right? And why is that? Because that has the most amount of information, most amount of surprise, right? The minute it is biased, then you can start making predictions, right? And therefore entropy goes down, right? Okay, so you have a file of 1 million flips of a perfectly fair coin, zeros and ones. Zeros, it's a head, tails, it's a 1, or vice versa, right? B contains the same thing, but it's 99% heads, 1% tails, right? Why 125 kilobytes? Why is that the size of the file? Trivial. Come on. My question is, why is the file 125 kilobytes?
Compressed.
No, not compressed. 8 bits is 1 byte. 1 million divided by 8 is 125,000, roughly. Okay, sorry. Okay, if you compress the file, which one will compress more? File A or file B?
Compressed more, that is file B.
File B, right? And why is that?
Perfect name.
No, so it is predominantly,
Rigged coin.
yeah, so it's like 99% of the data is all zeros. If a 0 represents a head, 99% is all zeros. right? The remaining 1% you can figure out how you want to encode it. Maybe just write the positions or whatever, right? Everyone okay with that? Yeah. How does the Shannon entropy of the rigged coin dictate the final file size? It's what you said in the previous. Well, or even in general, the lower entropy, the more you can compress it. There is less uncertainty. There's less information in the file, so you need fewer bits to represent the same information. All right. And then you can come up with multiple ways of this, right? How would you compress this file? You can do like a run length encoding, you know, number of zeros, then a one, or you could just say list out the positions where you have the ones, number of ways of doing that.
What is the best you can do?
Yes, it does.
But it may not be achievable.
Yeah, it gives you a lower bound. Not how to get there. Yeah. I mean, think about it, right? So, so it's 1 million. So 1% of that is 1,000, right? If you have those 1,000 evenly distributed versus bunched up at one end, the optimal algorithm and the optimal compression is going to be very different. So it depends on the pattern, right? Okay. What's the log used for IX? Why is the log used? Why do we use the log function? To convert probabilities into additive functions.
Otherwise, to count number of bits.
It gives you the number of bits, yeah, right? If a probability of 0.25, what is the self information? How many bits? Not 4. But good try. No, we can just plug it into the formula, right? So it will basically be 1/4 log 1/4. Nothing is showing up. Okay. Right. So what was the question? Yeah. Okay. So it's sorry. It's 1/2 log 1/4 plus 1/2 log 3/4.
1/4 log 1/4.
Okay. Sorry. 1/4 plus 3/4 log 3/4. Right. And then negative of that. So again, we have the 3, so I'm not sure how to do the calculation for that, right? But I believe the answer should be 2 bits for the 1/4 probability. Sorry, not 2 bits. It will be a value less than 1. That's the important thing. And why is it less than 1? Because it's a biased coin and you have less less information in the coin tosses. Okay. Okay. What does Shannon entropy physically represent in a communication system? Right? Again, the longest answer. How should you interpret h equal to 0.08 bits per event? Yeah, but out of these options, no. Actually, it's the opposite of the last one. because entropy is 0.08. So it's really, really low, right? So you can actually go through a process of elimination or use our regular algorithm. Physical transistors has got nothing to do with that, right? Channel is too noisy. We haven't talked about noise at all. Messages are completely unpredictable. Are the messages unpredictable if the entropy is 0.08? It's more predictable, right? Data is redundant. A perfect compression algorithm only needs 0.08 bits to represent each event, right? So again, longest answer wins. So that's okay. Okay, if you have a coin flip, at what probability does Shannon entropy reach its maximum value? 0.5, right? So at 1 and 0, it is completely predictable. There is no surprise if your probability is either of those, right? Okay. Yeah, and mathematical structure is identical to what? Right? Entropy and statistical mechanics. Okay. Let's see. Okay. So this is something that we are not deriving, but I want to discuss this formula and make sure you understand it, right? So we've looked at how do we capture the idea of information mathematically, right? I of x is negative log probability of x. And then also how do we capture the information content in a complete message or a string, right? And that's the entropy. Now what we're saying is if you're sending this signal over a particular transmission channel, can we quantify the performance of this channel? Can we quantify the maximum rate at which we can send this signal, right? And this actually is a very interesting formula. So if you look at these terms out here, B is the bandwidth. Actually, I have this written down. Okay, that's fine. B is the bandwidth. Sn is signal to noise, right? So we're going back to what we started out with, and you can and C is the channel capacity, right? So you can see what's going to happen if your signal is 0 or you have too much noise. This basically becomes log of 1, which is 0, right? So you can't transmit anything if you have too much noise. Your bandwidth of your channel is fixed, right? So for a given signal to noise ratio, this puts a limit on how fast you can send your data across on that particular channel. If you want to do better, either reduce the noise or increase your signal. I don't know actually. I'm not sure. It says it's a theorem, so I'm guessing it's not empirical, right? Okay. Now the other thing that you can do is if you have if this right hand side is less than the channel capacity that you have, then you can start adding a lot of redundancy to compensate for noise, right? You can do error detection, or if you have enough bits, you can do error correction as well. Okay. Let's see. I want to talk about this, so I need to share. So this formula is talking about the transmission limit, right? What we can also do is say, what about the processing limit, right? Can we, so this puts a bound on how fast we can send a signal or data. So can we think about what happens is there a limit? Well, it's not quite a limit, but can we understand what are the practical limits to processing information? Right. So for that, what we're going to do is we're going to look at what we talked about a couple of units back, where we're going to relate Shannon's entropy, which is given by this formula, to the thermodynamic entropy, which is given by this formula. Okay. And something really interesting pops out that relates to a question that you had asked in the morning, right? So suppose suppose I'm transmitting a bit through a channel, right? On the receiving side, at the beginning, I don't know what I'm going to receive, right? So my knowledge about what the message is very high, is very low. I don't know anything. Once I receive the message and read it, right, my knowledge has increased drastically, right? What has happened to, how has my entropy changed between those two? Has it gone up or has it gone down? And why has it gone down? I have more information, right? So my probability is now much higher. But there's a negative sign out there, but then there's compensated by the log, right? So if my entropy has gone down, now if I think of it in terms of thermodynamics, what happens when my entropy goes down? So physicists. So in any system, right, if my entropy changes, there is more order, but actually, wait. I may have gotten this wrong. If entropy goes down, it releases energy, right?
No, you have to put in energy to reduce.
Okay, then it's the other way around. So the point is, in whichever direction, so wait, it's the opposite.
You have to put in energy to
Yeah. No, but just if in terms of entropy, like without even work and heat. Yeah, exactly. Yeah, so if entropy goes down, you're releasing heat. The system is releasing heat. Right? You guys get that? In thermodynamics, if the amount of disorder reduces, right, entropy goes down, you necessarily have to release heat into the environment to absorb the heat. Out here, the same thing, we apply the same analogy out here. If I am going into a situation where my Shannon entropy is reducing, I have to release heat into the environment. You guys get that? Okay. Let's think about this for a second. If I have an AND gate, right, and my output is a 1, what does it tell me about the inputs? 1, 1, right? If my output is 0, there are 3 possible, we don't know what the input was, right? So that is an example of your entropy changing, right? The AND gate is an example of a gate that is not reversible, because looking at the output, we cannot figure out what the inputs were, right? And so through this equivalence, what this means is if you have a reversible gate, an irreversible gate, right, you are always going to be releasing, no matter how smartly you design your circuit or implement that logic gate, you are always going to be releasing energy into the environment, right, which makes classical computing extremely inefficient. All right? Okay. Yes, please. Yes, please.
Very confused. That's what you take a pack of cards, order it in the usual way, 13. That's a highly ordered system. Lowest entropy. Design whatever the color combination.
Shuffle.
Entropy has gone up. So as we said, if the entropy has gone up, now if I want to bring it back to the original one, I have to do work. So what he says, I'm putting in energy, bringing the cards back to the
Ordered
lowest
state.
entropy state.
Yeah.
That's exactly what
Yeah.
we didn't say.
Yeah. No, absolutely.
That you put the system.
Yeah.
You go to, so how do you resolve this? And just think about it. I mean, this is one of the ways that we ask questions.
So I mean, this is, no, that's actually a great point, because
I know. I mean, I'm not going to answer that at this time. Think about it.
no, but also to add on that, so that's where the equivalence between work and energy also comes in, right? So you could either cool the system or you could put work into it, or vice versa. So, okay. Let's see, is there anything additional? Yeah. Okay. So the equations are there on the website. So it basically talks about this, but this last equation is the important one, right? The amount of heat that is going to be released is dependent on the temperature that you're in, and again Boltzmann's constant, right? So what we can do next is we can say, hey, if I have this gate or if I have this system, right, where I have registers and I have bits at zeros and ones, right? If I force all of these guys to 0, that's not what it's, okay, reset all to 0. There were 3 of them, so I am releasing 3 times kBT log 2 units of energy, right? And if this makes you happy, you can keep resetting this and trying it out and seeing the number go up. If you find that entertaining, I guess go for it. This actually I need to remove this because it's not. I don't think it works correctly. Yeah, never mind about this. Okay. Okay. So you have a logic circuit that relies on multiple multi-input gates like AND and OR, right? It takes 2 binary inputs, produces 1 output. If it's a stable output of 0, the states could have been 0, 0, 0, 1, 1, 0. This is a regular AND gate, right? So has this logical operation preserved information or destroyed it? So for an AND gate, if you give any of these inputs, the output is a 0, right? So have we preserved information or have we destroyed information?
Destroyed.
Sorry?
Destroyed.
We've destroyed information, right? When you look at the 0, you have no idea whether it was what the outputs, what the inputs was, right? Why should an irreversible computer chip generate thermal heat even if we build its physical transistors of frictionless perfect superconducting materials? Because of this, the entropy has changed and that has to be manifested in some way. All right, everyone okay with that? And now the most important question out here, how would you design a computing structure that performs calculations without violating what we just saw? That's called Landor's boundary, Landor's principle. Is that the right pronunciation? Okay. What structural rules must the logic gate satisfy? Yes. You see now why, right? So it's not why quantum computing does reverse. We'll see that also in a second, but it's related, right? And quantum gates have this property that they are reversible, right? Except when we measure it. That is not reversible, right? Okay. I'm hoping.
They will consume less energy.
Huh?
They will consume less energy.
Who will consume less energy?
These gates, quantum gates.
Yes, compared to classical gates, yeah, at a theoretical level. Because in order to apply a quantum gate, right? Exactly, yeah. But from a thermodynamic principle perspective, you're not losing information using quantum computing the way you're losing information in a classical computing sense. That energy loss is not there, right? I think let's skip this. There's one very important thing I want to do. So this is something that you've heard over and over again. So I'll go through this very quickly except for the next section. So in quantum computing, instead of looking at zeros and ones, we are looking at a superposition of zeros and ones.
1 minute.
Yes.
The comment that you made regarding a quantum gate being reversible.
Yeah.
And that is fine. The fact that the classical gates are not reversible is mainly because of the way information is represented.
Yes.
Because there I just represent either bit 0 or 1.
Uh,
Whereas in quantum, we represent probabilities of 0 or 1 basically. So
Okay.
It's a question of basically the amount of information itself was not there to start with.
No, I disagree. Because if you take an AND gate, right, you have 2 inputs.
No, I'm not talking about AND gate.
No, I'm giving an example. When you have two inputs 0 and 1, you know exactly, you have the complete picture of the input space. Input 0 is 0, input 1 is 1. There is no ambiguity out there.
Actually, my point, maybe we'll discuss offline. My point was, it's not about the gate, it's about the bit 0 and 1 represented. So 0 is
Well,
just a single 0,
right.
it is just a single 1. Whereas we say gate 0 like
Yeah,
that.
yeah.
So when I say gate 0, essentially I'm giving probability of it being 0 and probability of it being 1, something like that.
Well, okay, so just ask this question again after the next section.
Okay.
No, that's a very good point. Let's discuss it after we talk about the block sphere, right? Okay, so all of this stuff you guys know. Alpha ket 0, beta ket 1. Alpha squared plus beta squared has to be equal to 1, represent probabilities. If alpha and beta were real numbers, right, we could represent psi as a vector on a two-dimensional plane. 0 would be your x-axis, ket 1 would be my y-axis, and the length of the vector is alpha squared plus beta squared, which is 1. So in that sense, this vector lies on the unit circle on a two-dimensional plane if alpha and beta are numbers. Okay. Now, in quantum computing or quantum mechanics, alpha and beta are not real numbers, they are complex numbers, right? If we say alpha is a complex number, it is a plus beta is some x plus yi. So we have 4 parameters. So the question is, how do we represent that? How do we visualize what this psi looks like? And that's where the block sphere becomes really, really useful. It's good for representing one vector, but it gives us a lot of benefit in terms of how we interpret qubits, and I want to share that with you. Not completely a topic of information theory, but I think it's worth looking at. Okay, so okay, so this is a repetition of what I alpha ket 0, ket 1, they're complex numbers. I have 4 variables or 4 degrees of freedom, right? The nice thing is I still have this condition, alpha squared plus beta squared is equal to 1, right? So really speaking, I have only 3 degrees of freedom. Technically, I could represent that in a 3-dimensional space, technically, right? But I can actually do better than that. I'm not going to go through the entire derivation, right? But I'll give you the highlights. My a plus bi is a complex number. I can represent as polar form, magnitude and angle, right? So I'll have R1 angle gamma or e raised to gamma, right? So vectors are gamma. But guess what? When I represent this, when I R1 e raised to and betas R2 e raised to gamma 2, I can actually multiply it. So this will just be R1 and this is R2 e raised to I phi. Okay. Now it turns out that this particular thing doesn't matter to our representation. Go into the details right, but I can write this as psi, and now look, I have R1, 2 and 3. I have 3 things that I have to represent. Okay. Even in this, I still claim that R1 squared plus R2 squared is equal to 1. Find R2. Really speaking, there are only 2 things that I need to plot, right? The R, once I know R1, I know R2, right? And the phi. Okay. So now if I'm saying, you know, look at R1 and R2 e raised to I phi, it's not R1 squared plus squared, but even taking the square of this is going to give me what? E raised to I e raised to minus is going to 1, right? So have R1 squared plus R2 squared equal to 1, I can actually write that as cos theta and sin theta. Cos squared theta plus sin squared theta is equal to 1, right? And for notational convenience, I'm of theta. Okay. Now represent becomes P is cos theta by 2 ket 0 e raised to I in theta by 2 ket 1. Okay? Now you could say, okay, hey, I've got only 2 parameters and phi. So I can still do it on a 2-dimensional plane, but we are still going to use a 3-dimensional representation. Two angles, theta and so we need to figure out how we are going to plot it. Okay? As before, these two represent the probability, if I were to measure it, the probability of ket 0 and ket 1. It's the same as before, where theta is the probability of getting ket 0 and sine square theta. This e raised to I phi is really important. It gives us the phase of psi. And phase is, morning when we were looking at Deutsch's theorem, we had A or alpha 0 plus beta ket 1 and 0 minus beta 1, right? Both of those, if we were to measure, we would get ket 0 with what? Alpha squared. Ket 1 with what probability? Beta squared. So if I were just to measure those two, I won't be able to that minus sign between ket 0 plus ket 1 and ket 0 minus ket 1, that is that phase, right? And the way to measure it, like Professor Zog said, to project it onto a different computational basis, but we'll get to that. Okay, so let's see how we can plot these guys, right? So what I'm going to do is my horizontal, my positive axis as my reference. I'm going to call that ket 0, okay? And theta is tell me the angle from ket 0. So if I go all the way down, I've gone how many radians? In normal space, if I go this is pi radians, right? If I go halfway, that would be pi by. Okay, so out here, this is 0, this is ket 1, and if you those values, so theta is equal to 0 pi, and if you plug in the values out here, sorry, yeah, in the values out here, if theta is 0, this is 1, 0, so I just get ket 0, and if theta is pi, this is cos of pi by 2, which is 0, pi by 2 is, so I get ket 1, all right? Gish, you see how ket 0, ket, we were talking about lunch, and on the T plane, ket 0 and ket 1 are orthogonal to each other if alpha is reals, and the question was how come they are opposite each other in the plane. That's why. Okay, the phi do. So let's rotate this 90 degrees, pi by 2 radians, right? So this ket 0 to, so this is like a horizontal plane, if you can imagine that, right? So we are in this plane. So this is now in the plane, any vector in this plane is going to be at an angle of pi, right? But how this vector is oriented in this plane is defined by that phi, right? The phase to I, that phase is determined by the orientation of the vector in that plane, in the xy plane. Get this? Okay, so let's start from 0, right? If I rotate this vector 90 degrees, it is going to be on this horizontal plane, okay? So if you look at this guy, so the plane determined by these axes, right? So when it goes down by 90 degrees, if you think of this equatorial circle, right, that vector anywhere on that equatorial circle, all of those vectors are orthogonal to ket 0, okay? But the orientation in that circle is determined by the phi. That is a, you guys get that? And so you looked at those poly gates. Z and all of that, or the Hadamard gate, right? Take ket 0, you can map it to ket plus or ket minus, right? Or you can also map it to ket I and ket negative I. Okay? The only is the e raised to I phi, right? So this is expansion of what I just said. So you take ket Z, this guy is they're all 1 upon 2. Any vector on this plane, if you measure it, probability of getting ket 0 is how much? 1 by root 2 squared, half. And the probability of ket 1 is the same. But they are all vectors. There is a difference, plus and minus, and I and negative I. All right. And now you can expand that to this diagram that I am inordinately proud of. So one is, okay, I can look at different vectors. So this is ket 0, ket plus, ket minus, ket I and ket negative I. So these are standard ket. But I can also change theta. Yeah.
When you say ket 1 is diagram opposite,
Yes.
is it in a different plane?
A different plane.
It looks like that because it's a 2D.
No, so this is a 3D project. It's a 3D. It's a sphere.
Right. So
The
that one that you are showing, not equal to ket 0.
no, this is the north. Here, this is the south pole of the sphere. It's opposite to orthogonal. Mathematically, it is. This diagram. That's why we use cos of theta by 2 and theta by 2. So if you go pi by 2 pi degree, right, you come to the bottom. You're downwards, right? But you'll see why in a so yeah. Yes. This is there. I mean, it's LMS, right? You can log in. You can play around with. Thank you, Kunj, right? This is the really cool thing, right? If I take intermediate value of theta, right? Just imagine that I have something pointing and I rotate it like this, right? So for the same theta, I can vary the field, right? And if you can actually rotate this, if you want to look at it from the top, you'll see it full rotation. All right. So this is the sense in which blocks represents the size. So now I wanted to talk about something that came up in the conversation this morning. I don't remember with whom. Now just think about this, right? I have a vector, so it's pointing to some point on the sphere because the vector is 1, right? What happens when I multiply this vector with a matrix? What is a matrix applied to a vector? It's a linear transform. So it is going to map that point to somewhere else on the sphere itself, right? And now, if I can map a vector from one point to another point on the sphere, I can easily figure out how to go to the origin. Using what matrix? The inverse of my original matrix, right? So if quantum computation is basically taking a vector and moving around on the sphere, you see why it is reversible. Because I'm basically applying a linear transform, I can do the inverse transform to where I was before, right? So it kind of nicely comes all together when you think of it in this. Okay, I want to add one more. This was a personal aha moment for me, and I think it will resonate with most of the non-physicists out here. because the physicists already understand this. First, when I think of logic and a circuit, right? I have inputs, I have of logic gates, I have an output. What's happening is apply the inputs, the electrical signal moving these gates to the output. That is that I have in my mind, and it fits the way we are, right? When I initially started looking at quantum computation, this confused me a lot because we draw the circuit in the same. I have qubits, I have the gates, and then I do measurement on the other side, right? But this is different what is happening in reality, right? What's happening is the qubit is not going through the gates, through the different levels to the output. The qubit stays is we apply the gate to the qubit. Qubit moves around, it changes its states, it changes the alpha beta, right? So this is evolution in time. Our regular classical circuits are evolution in space. Happening in quantum computing is evolution in time. We have qubit physically in one place, we are applying gates to it, which are transformed. They are changing the state of the qubit. And then eventually at some point, we measure it, we say, okay, this is out.
Maybe I will come back to the question again.
Yes. Yeah, this is the good time to.
So now look at it, what is actually happening in the whatever so-called classical digital circuits, we are dealing with single dimension.
Yes.
Just 0 or 1.
Yes.
No notion of.
Yes.
What has happened perhaps in Q is that you have both the dimensions. By saying that there is x and y,
Right.
the qubit is basically something which has some component on axis and some y axis.
Yes.
Because that information is present, that's the transformation. So the information has lost because the representation itself was faulty in a way.
I agree with. I'm trying to articulate why.
I think the question came from that AND gates. When he said that one, it lost the information because the answer was 0. In the AND, that's where it started actually. So, and then he said that it doesn't happen in the quantum.
Yeah.
My submission is that, and maybe I'm wrong, just throwing it basically, that my submission, one right is the information representation itself. I mean, the bit 0 and 1.
Right.
You still have quantum. Representation
Yeah.
of 0 and 1 bit is different.
Sure.
You have that gate where the column matrix, and you say that the value which you have is essentially the probability of the 0, so-called bit 0. The second one is the probability of bit 1. Now, understand it.
Right.
Now, so what you have but it is required in quantum because it's really, it takes probability.
So I think the problem is trying to equate the two representations.
Okay, let me put in a very little bit philosophical way.
Yeah.
The same reality that we are dealing with.
It is not the same reality. That's a good point.
When you have a situation, it is simultaneously in both the.
I agree. I understand.
No, but sir, so that's why it's not the same representation. That's the point.
I'm just wondering whether that loss of information was because of the representation or
So,
because of the.
No, you could construct a classical circuit with no loss of information.
And
You can do
how
that. The way we construct x and f of x XOR y, implement classical logic. That is possible, right? So it's not a function of the representation. It can be implemented like that, right? But I think going to what Professor Zog was saying, you're representing two very different things. So we can't equate 0, 1 in the classical phase with that.
take his word
Yeah.
because the probabilities themselves are not classical.
Yeah. Yeah.
Quantum superposition, the probabilities are not proper. They are absolute. And you will get.
Yeah.
Yeah.
That's what I'm saying, that you are talking about combination probabilities. That's not.
No, it's amplitude.
It's amplitude. And you see, when you make a measurement, you will any one of For example, in the case, two-state case, it's like both the states correct. This is yeah. This has no classical analog. Same. No classical. So that is the basic difference. I mean, you can different from this. That you have to deal with the fundamental that will define you can extract
From this. I think Avik also wanted to say something. Classical circuits, yeah. Is that this? Yeah. Okay. So the last point to make out here, this is something we talked about over lunch. So if I take this this bit or the state psi, in regular classical circuits we have n inputs. There are 2 raised to n possible combinations, raised to 2 raised to n different functions that we can define, right? And therefore, you know, the number of gates is defined by that. Number of functions is the number of gates. How many gates can we have out here? Infinite, because that vector can be modeled to point on the block sphere. So there's an infinite number of that I can. It's not just fixed to like a limited number. Later on, but okay. Is this fine? Like, do you guys I mean, I know you've seen block sphere before. Does this help? Yes. Yeah.
So, in terms of the gate computing, then are all the gates reversible? Is that right?
I believe they would be, because you can point. So as long as you're not reducing the dimension.
Every quantum gate is reversible.
Reversible, right? Yeah. Right? Yeah, measurement. Because in a way to think of it is, if I move from one space to another point.
True, but that analogy then doesn't tell you why 2-qubit gates are also reversible.
Okay, thanks for bringing that up. Block sphere cannot be represent 2-qubit systems, right? And that because of entanglement. If you had 2-qubit systems that were independent, right, and that you could multiply to get the state, then you can. But because of entanglement, you can't. Everyone okay with that? Yeah. Okay. If I have a critical bit, it's only at the north pole or the south pole. Qubit can exist anywhere on the surface. How many bits of information are in the precise coordinate of that vector compared to a single class bit? So it's actually wrong to say how many bits of information. Well, qubit is just one. Right. So okay, so you could say one bit of information, but basically the alpha and the beta, right? The theta, I guess that's a better way of thinking. But because they're real numbers, I mean, how do you say qubit? Okay. Why do we describe the qubit as existing in a combination rather than it's saying it's partially 0, partially? It's not any of those states, it's in a combination of those states, right? Only one of them, of both. Okay, this is good. Perform a rotation on the block sphere. Have we changed the probability of measuring 0? Yes or no? Right, because we are like that. Probability of 0 and 1 is exactly the same. We've only relative. Well, we're talking about the phi. We're talking about phi. Yeah. Right. Why would you care about the phase in the problem? Professor Zog is saying we've discussed this. Better answer. Right. So that's for you guys. Chandra to ask that question. So I'll actually show you another conversation I had in. It was so frustrating. Uh, uh, I'll just copy this entire thing. So the reason it's frustrating, I'm going to ask about what I think about something. You guys know about ELIZA? So it's Chandra acts a little bit like that. Actually gave good. Yeah. So for me, this is the main thing. Creates environments, and those actually give us a lot of information that we, right? But yes, Chandra actually worked very nicely out here. So ELIZA used to like if log in, how are you feeling? Yes, if you say how are you feeling, you say I'm feeling. Why good? So because I had fun. Oh, what fun I have? Yeah. So here, I'll show you the conversation I had. It was in the next section, and basically asking it about. So you have Turing machines for classical complexity theory, and I'm thinking what is the equivalent for quantum? And it said, oh, let's think about this. What is unique about quantum? And then it was trying to get to develop the whole theory of a quantum Turing machine. Finally, I just went to Gemini and I asked her the question. But anyway, that's the sense in which I said it's a lot like ELIZA. Okay. I think that is, yeah, I think the quiz is fine. It's stuff that you've seen before, so we should be good. And this actually talks, okay, so let me, so the last, I'm just going to skim over very quickly. What I wanted to point out is in terms of differences, between classical and quantum information theory. So for a classical system, the state system is the sum of its parts, right? The quantum system, it's not, because of entanglement, right? That's one difference. And this actually came to my mind when we were talking about something this morning. I have a system like this, right? Maximally, right? Why do I claim that the state is not the parts? Because I have two qubits. This is qubit 0 and qubit 1. If I enter qubit 0, I know exactly, I know everything there is for qubit 1. You guys agree with that? State of the other qubit. You guys or not? Nobody's looking up, they're all like something down. So if I measure this particular psi, if only the first qubit of psi is a system, I measure the first qubit, I get a 0, right? What does it tell me about the other qubit? It has to be 0. You don't even have to, it is definitely going to be a 0. So that's the sense which, if you think about the amount of information in a classical 2-bit system versus an entangled 2-bit system, it's going to be very different, right? Have we talked about the no cloning theorem? Okay. Next, okay, so we are going to talk about cloning theorem. So I haven't put anything out here, but basically, one very popular and fell for actually was okay. So measurement going to collapse the qubit to a 0 or a 1 to destroy the state that we had. So then why make a copy of it, right? So I can continue processing with a copy and I can use the original to measure. Does that make sense? So the no cloning theorem tells us that we, right, literally because of the name, clone qubit, and this is in fact one of the reasons why encryption becomes so powerful. Detection of copying becomes very powerful, because if you have if you send a message as a qubit, yeah, so somebody is listening and they're making a copy, it affects the state of the qubit that you're transmitting, and you can detect that at the receiving end. Copy cannot be made. Yeah. Once you measure it, it collapses, right? And then is this whole entropy business. Okay, so let's have 7 minutes. If you guys are okay to start talking about, so I have two slides where I want to talk about computational complexity in the context of quantum computing. I'll start the basic. I'll continue in the next session, right? Okay. You guys know about computational complexity? Very open question. What are the terms that come to mind?
Time and space.
Requirement. Keep going. Keep going. Time, space requirement. Or asymptotic is. What else were you saying?
P space, NPP.
P space, NPP, or defined. What rotations? Sorry, what is that? Big O. Oh, big O. Yes. Big O, asymptotic analysis. Yes. And P is defined in terms of Church-Turing thesis and Turing machines. Sorry? Halting problem? Yeah. Halting problem is an example of a problem. No, it's not NP. Well, sorry. It's undecidable, right? NP. But why do we need Turing machines? It's a model of computation. It's a mathematical model of computation, which allows us to define time complexity and space complexity, right? Is everyone familiar with Turing machine? Okay. You need a common frame of reference. Yeah. Turing machine, right? So Turing machine is a very simple machine. As it's a state machine, right? So you can bunch of states, let's say Q0, Q1, Q2, and define a bunch of states. If my input is 1 and I'm in state 0, I'll go to state 1. If input is a 1 in state Q0, I'll go to state 2 or Q2, right? So I can define the transition function. Turing machine expands on this definition. What I described is basically a finite data. But a Turing machine also has, let me draw. So the not important, but I think it's a good. It will give you a frame of reference. So Turing has some control logic, and it has finite tape. Okay, and this tape. So control has a head. Along with the state machine that I talked about, basically read a symbol on the tape based on what. So when I input 0 of the input is 1, in that instead of that something that is written on the tape, and based on the state itself, it will do 2-3 things. One is it will transition to new state. The second is it will maybe write something onto this cell, may or may write something, and the third thing is it will move left. Okay. Yes. So it's called a read-write head, right? So that is the Turing machine, and I can define it mathematically, a 7 tuple or whatever, but that's not important, right? The point is that something this simple, so Turing proposed this machine. Franz Church defined something called the lambda calculus, and I think 1936. So before computers were physically realized, imagine. So this is like pure mathematics. What they showed is the calculus and Turing machines are equivalent, but important, any model, any reason model of that we have today, right? Century or 90 years after the was proposed, is equivalent to this model. This is really amazing. So all the machines that all the architectures and vacuum tubes and CMOS transistors and 8086 and power PC, all of that is equal to this. Okay, it looks like a really dark architecture and very slow, but it's not meant to be a practical architecture. It is meant to represent a abstraction of computation do, right? So when we talk, so some of the terms that were space, time and complexity and all of that, we can define that in terms of this machine. So for example, say an algorithm takes so much time, right? That would be similar to saying how many steps is the head moving in the execution of the algorithm. Okay, that's one example of how we use the definition of the Turing machine. If I want to think about space, right, I can say how many of this tape are being used. So you can give me a sense of how what the space complexity of the algorithm is. Okay, and a standard example of the following. Suppose I wanted to create all possible chess games, right? Number of possible for white, 18. Got 8 pawns, they can move 1 step or 2 steps. Knight can also, so it's 20. The knight to 2 knights, 2, okay. And then can respond on 20. So already we are at 20 into 20, just at 1. Then for that, move 2 white. So number of moves grows exponentially, right? The running time of, if I wanted to simulate all possible chess games, the running time is exponential. What about the space?
It's finite.
8 by 8, right? It is because whatever moves I'm making, it's happening on the same board. I need only 64 space for that. So that's an example where I can have an algorithm that's in exponential time, but requires a finite amount of space. Okay. I went out of order. The first thing I should have said is P is NP. One of the most important, it's important, but one of the most about problems in complexity theory, right? So we look at different problems, classify them as P or NP. There's actually levels in between that as well. But P stands deterministic polynomial, NP stand for not polynomial, non-deterministic polynomial time, right? That means if I have an algorithm that runs in polynomial time, a deterministic Turing machine. Deterministic means if I am in a particular state and I get there is only one output and symbol that I will write and movement that I will make. There's only, it's fixed out, the next fixed, right? Non-deterministic is when I could go here, I could go to state Q1, I could go to Q2, I could go to state Q3, right? And then in those again I could branch out, right? And then through that branch, if I reach a place where I find the solution, and I say that's my solution, or I could expand and never reach, as well, right? So a non-deterministic Turing is not feasible. It's an abstraction, right? It gives a very good way of classifying problems, things that can be solved and things that are easy to solve and that are not easy to solve. No. Is not probabilistic. So we are saying that I have 3 possibilities. I'm going to explore all 3 possibilities. I'm going to explore the entire thing. So I'm not choosing the other. I'm going through all of them, right? And then I'm expanding all the way out. So Markovian or yeah, those have probabilities. Like you choose just one of them. This is not probabilistic. Sorry. Say Markov chains, I'm thinking of the matrix multiplication. So you just, okay, right. Yeah. No, but is it empty those states, right? When you do the multiplication, I've done this like 20 years ago, so my memory is very big about it.
The one which only remembers
the previous.
The probability of going to the next step is
Oh, right. Yes. A Markov process. The probability of the next only depends on where you are right now. Yeah. Okay. Yes. Yeah.
Another way we can state there is input or multiplication.
Yes.
That is non-determinate.
Yes. Thing is, exploring all of those.
There is a
Yes, absolutely. So why the deterministic Turing machine upset deterministic Turing machine, right? You have only position, absolutely, right? Okay. So back to what we were saying. So the class of problems that can be solved in polynomial time on a deterministic Turing machine are problems that are in a sense easy to solve, right? It takes a polynomial amount of time to solve, right? If we don't have a polynomial time algorithm, right, does that mean not belong to P? I have a problem, right, and I only know a algorithm to solve it on a deterministic right? So does that mean that it does not belong to P? Well, no, but I think so. What I was getting at is just because we don't know a problem, just because we don't know an algorithm, doesn't mean it doesn't exist. Okay. What is an example of a problem that requires exponential to solve? Oh, time, right? Exponential time. Long is not normal, but the standard example is satisfiability. So, and in fact, very precise 3-sat, right? So, if I have a formula which looks like this, x1 plus x1, I'll use plus and dot, plus 2 plus x3 bar and x2 bar plus x4 plus x bar and so on. Is there an assignment? So all the are Boolean variables, right? Is there a assignment of true or false values to all the x's such that this formula equates to true? Why each of these terms has 3 literals, right? And this conjunction of the disjunction. So it's 3 as well, conjunctive normal form. Okay. So it turns out that only way or the only known algorithm that we have solving this is to try all possible values. brute force. So you try all.
In conjunctive normal form, same or it can be any.
In 3 it's 3. It could be anything, but then it won't be 3 sat. Sat is possible. Satisfiability.
Actually, they are saying even not doable.
Yeah.
I mean, the general is not doable. That is not doable.
Yeah.
That is
No. So I can have x. Those are Boolean literals, right? So so I could start with all the false, 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 true, false, 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 true, false. Keep all the way to true, 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 right? How many combinations are there? There of these from 0, 0 to 1, 1. No, if I have n, yeah, it's to n, right? Because each variable can take true or false. So I have 2 choices for x1, 2 choices for x2, 2 choices for x3, 2 choices for x4, all the way to xn. So 2 into 2, 2. If I do the brute force method, time is 2 exponential. Mean that is no polynomial time algorithm? Maybe it is. But in the last 50 years almost, 57 years, nobody's been able to figure out one. So in general, if I were to look at the class of problems, right, I have, so the problem can be solved in polynomial time on deterministic machine. And then I have a class of problem won't go into the hard NP and all, but I talk about different problem, right? It is called BPP. Anyone know what that stands for? So by the way, there is also P space, which typically is kind of, right? So there are problems, actually I'm not sure if it encompasses it or if it's intersection. No, I think it's probably an intersection.
intersection is NP hard.
No, so I'm not going into NP hard and NP complete. I think this much is fine. But what is BPP? It's a very interesting class of problems. It stands for bounded error probabilistic polynomial time, right? So these are problems where we can, and this ties into a discussion that we were having last week. These are problems where you can, these are classical algorithms, right? It's not quantum. We haven't gone to quantum yet. Classical algorithm where you can calculate the answer with a certain probability of it being correct. Okay? The best example for this is something called the Miller-Rabin test for primality. So if you give it like a, like if you take a big number like 512 bits or 1024 bits, right? How do you test whether that number is prime or not? What algorithm would you use, or how would you solve, how would you check whether a number is prime? Factor it. How would you factor it? Efficiently?
Go up to the square root.
Go up to the square root and exhaustively try all the prime numbers, right? You see, is it divisible by 2, 3, 5, 7, 11, 13, 17, right? You try everything all the way to square root of n, right? Exponential time complexity.
We have AKS also.
So until, yeah, so okay, step by step. So before we had AKS, we had something called the Miller-Rabin test, which tells you if a given number is prime or not with a certain probability, right? So this belongs to something called BPP, which is with a certain probability, it will tell you the answer is correct or not. There are again variations in there, but let's not get into that. And as it turns out, around 2001 or 2001, there was this paper which I feel has the best title of any paper that I've ever seen, right? And the title is Primes is in P. That's it. You see the title and you know exactly what the paper is about. I've never seen anything like that, right?
There was another distinction, perhaps that was the first crowdsource verified paper.
Or the verification, okay,
So,
yeah.
so they released it only to the academicians.
Right, right.
And within 2 days, everyone said that it is proved.
It is correct,
And
yeah.
then it was put up in journal and conference later.
Yeah, yeah. I didn't know that. I didn't know that. I do know like they.
Part of that is.
Oh, you are
I
okay.
got that one copy.
Okay.
One of my professors in IIT.
Right. No, I didn't know that. I do know that they were able to improve on the algorithm very fast, very quickly.
They were second year
So,
students. Second year BTech
yeah.
students.
So, by the way, this is AKS are students from Kanpur, right? IIT Kanpur. Yeah, the A is Agarwal. The other two guys were.
Manindra Agarwal, who is currently director.
Yeah.
IIT Kanpur. Then Nitin Saxena and Katyal, some Katyal.
Katyal. So they were both undergrad students.
And one of them is
Right.
right now professor at IIT Kanpur.
There you go. Yeah. I think they're both in India itself.
No,
Or-
yeah, both in India, but
yeah.
one guy is in Google, the other guy is in probably
in back in Kanpur, yeah, right. So this is like a proper Indian achievement, or however you want to call it, right? So it's called the AKS proof for the AKS paper, right, for the authors of that paper. But so the point was that we didn't know a polynomial time algorithm until these guys were able to come up with it, and then so we knew primes was out here, but they showed that it's actually in P. So just because we don't have an algorithm doesn't mean it's not there. But more relevant to what I was talking about in terms of BPP, there is this Miller-Rabin test where you can show that, or you can have some amount of confidence that a number is prime or not prime based on that particular algorithm, right? One example of this that I really like is the following. So suppose I want to verify A, B and C are n by n matrices, right? And I want to check whether A into B is indeed equal to C, right? How would I do this? I would actually multiply the two matrices and compare it with the third, right? What is the cost of matrix multiplication? N by n matrix, n cubed, right? If I want to be over smart, I would say n raised to 2.7 or 37 or whatever. Okay, but like if you want to say Strassons or use tensor products or whatever, but in general n cubed, right? Here's one way of doing this in a probabilistic manner. So I can define a vector x, right, of length n, a random vector, and I can calculate b into x. How much time will that take? Well, n rows into one column. So that will be order n squared, right? And then what bx gives me is a vector of size n. So I can multiply that with a, which will also be n squared, right? And then I can also multiply c with the same vector, which is also n squared. So in 3n squared time, right, I can verify if these are equal, that has to mean a into b is equal to c for that value of x. That's very important, for that value of x, right? And now you can generate more x's randomly and you can keep doing this. So basically in time order kn squared, I can do this verification instead of order n cubed. And there is a mathematical analysis which shows that the probability of A into B not being equal to C, right, even though this works out, keeps decreasing as you keep increasing the value of K. So you can bound the probability of getting a wrong answer.
The significance of KB.
So the more you do it, the more iterations.
Physical significance.
Uh,
It is what is? Can I say K is the number of times I check this property, for example?
The number of times. Well, so K is the number of times you're using this particular test. The number of random vectors that you're trying.
Yeah.
Right.
Then
So in the extreme, if you were to try n vectors.
So n is the upper bound.
Yeah, if you were to try n vectors, then your running time would become n cubed.
Yeah, true. But then
Right.
in that case, that n vectors that I'm trying should be exhaustive. I mean complete.
True, but the point is you don't want to go to n.
I'm just guessing.
Yeah.
Maybe I'm wrong. So does it mean that those n vectors that I generate?
Yeah.
It's a vector of size n, single vector of size n. I think x. That is what x.
Yeah, yeah.
So I think I should just change the. I mean, put all zeros and put one non-zero at only one of the places.
So, okay, ideally you want to use a completely random vector.
Okay.
Why? It ties in with the information stuff we talked about before. Because if you have all zeros and just one of them 1, right? Essentially you're just isolating one particular row of B.
So the question could be, suppose I try with one vector.
Yeah.
How do I generate the second vector which it is something different than what I already done?
So that's assuming you have a good PRNG. So, right. But actually there is a way of generating a vector of zeros and ones randomly, right? So that basically selects a certain number of rows of B, and then unka linear combination yeah. But anyway, so you know you could think of the extreme as K is equal to N. You don't want to do that. You want to keep K bounded, right? But the point is that this is an example of an algorithm that is in BPP, right? And in terms of complexity theory, people believe that P is equal to BPP. So if you have an algorithm that is in BPP, the overall consensus is that there is probably a polynomial time algorithm to solve this particular question. We just haven't figured it out yet.
They do give probability of accuracy as well?
Yes. They give you, it's a bounded probability. Yeah. Okay. So I think let's pause out here. It's almost 4 o'clock. Chaha hai ka? So the plan is please have chai, coffee, biscuits, and then follow a week. So are you going to do it here or there? Here. So come back here. 4 to 5 a week is going to demo our homegrown quantuper, right? So 2 things about it. So one is we want you guys to use it in your quantum computing course, right? Because it's really powerful to, rather than using a simulator, to run your code on an actual live quantum computer, right? So he's going to talk more about it. I'll leave that to him. But the second thing is he has designed a full project proposal of how you can build your own quantum computer in your institute. It's going to be small, 2 bits to start out with, but you can go up to 4 or 5 qubits, right? And there are lots of, so it's not like a step-by-step instruction, it doesn't detail everything out. There are a large number of areas where you guys can come up with solutions to different technical challenges, right? So Kunj has mentioned this before, I'm reiterating. This is a great example for you guys to go back and, you know, get people really excited to build a computer at your institute, right? This is going to require people to come in from all domains. You will need physics, you will need electronics, you will need computer science, right? So it's a great interdisciplinary project. So we encourage you to try that out. Okay? Okay. Get refreshed and let's continue.
The concept of density matrix comes in NMR because NMR, the physical system of NMR, which is the underlying system behind this front end, is ensemble. It gives an ensemble average. So it is slightly different from the usual quantum computer because is that let's take the example of Qiskit. In Qiskit, if you run the same thing and if you submit it in the hardware, it generally writes at the bottom the shots. That simply means that it has run n number of times. Okay. In NMR, since we are dealing with bulk sample, therefore we don't need to run it n number of times. In one time only, we are getting 10 to the power 9 outcome of 10 to the power computation on 10 to the power 9 molecules, and therefore what we get is a statistic average. Okay. So to represent a statistic system, we use density matrix. We that's clear, right? Therefore, we are showing the density matrix over here. Okay. So this is the simulation part. So a very simple example is I showed that if you are looking at the density matrix, this a density matrix, you will get something like this for a 2 cross ket. So what we have also added to that is that you can also emulate an NMR system. So before you submit your experiments to the hardware, which is here, explain the hardware. Okay. So before you submit that your experiment, you can also emulate that how will it look in an NMR system. So this is one place where we are kind of slightly varying from the existing available quantum computers, is that we are giving a flavor of the real computer output which a student can expect. Currently simulation, so we are simulating an NMR system, 2-qubit system. If you are having a entangled system, density matrix of this form, this is a bit complicated. So let's move on to simpler one. So if you just add a NOT in 0 0, you should get 1 0. So in this there are no coherences, there is only population. That means you will get the 0 state with probability 1. Okay. So the NMR spectrum would look like this. It like this, and this is what we are simulating. Why are we simulating it? That's because we do not expect a person who is learning quantum computation to be familiar with NMR. Okay. That is because to understand the NMR, he has to first have a basic course of quantum mechanics and an application of that. So once he simulates this, he can also run it on a real quantum computer. So this I will show by So currently this is a work in progress. So we have not implemented possible gates because it's not straightforward, because what we are doing is there is a front end which is talking to AWS backend, which is having all the maintaining the queue for the job submitted. So there it is connecting with a tabletop hardware system which is there in the lab over here. Over there we are writing the pulse sequence, which is different script. So the when we run a specific experiment, we are actually from the big script we are selecting some parts of it and running it. Okay. And once that is run on the hardware, we get the output. So for example, if I want to run a NOT gate starting from a 0 0 state, then what should be the output? So I can run it here. First I have simulated. Why can't I run it on the hardware? Okay, let's use this Proton. Yeah. So this is the spectrum that you should expect around hardware. So once I've clicked it, it will take time. It will take around 2 minutes. So in the meantime, I'll explain what we are doing it. So
once I've clicked it and it's running on the hardware, it means that it has gone to this system. We have exactly the same system in the 5th floor. It's an spectrometer. You mostly will see it in food pharma industry or drug discovery industries. Okay, and also it is basic principle behind MRI also. Okay, so it can also be used for quantum information processing. So the experiment is submitted here. Once we are submitting in the hardware, and it takes some time to run because okay, so I'll tell you what it is. So what is happening is in NMR is there are nuclear spins which have magnetic moment, right? So if you look at a atom, it will have electron. There is nucleus. Nucleus will have protons and neutrons. Each of them, depending upon the number of nucleons it has, it's even or odd, they may have a non-zero magnetic moment. And if they have non-zero magnetic moment, if you place them under a external magnetic field, they may align along the field just opposite to the field. And this is they take only 2 states because these are all spin half particles and they follow the usual quantum behavior. So this, since it is a spin angular momentum, for a spin half particle the number of possible states plus half and minus half. So what is done is that I'll break this whole animation. So initially at equilibrium, the whole polarization is along the z. The vertical axis is z convention, okay, and that is where external magnetic field denoted by B0 is present. That is the direction. Now, once a RF field is applied on it, so we choose RF field because the energy difference between the spin energy levels are of that order. Okay. So therefore, the resonance condition can occur only when we are applying RF frequency electromagnetic waves. So that is what we do. So we apply RF frequency electromagnetic waves that disperse the spin, and in this case it is going to the xy plane, okay, and it precedes about the main magnetic field. So once it's precessing, now the field RF is off because it was a pulse, okay, and the time of the pulse is chosen in such a way so that it comes horizontal plane, transverse plane and stops. Okay. So once it is precessing, there is nothing actually disturbing it. It try to go back to equilibrium, and that is what is shown over here. This spin slowly goes back to equilibrium. However, the thing to note over here is that great, thank you. So, yeah, so basically what is happening is there is a oscillating field because the magnet is rotating. Okay, so this is clear, right? Why the field is oscillating, the voltage, because we have a Faraday's laws of induction. Because if you rotate a
magnetic field is along the z axis.
there is a large magnetic field. I am talking about the nuclear spin which is now in the xy plane and it is precessing about the big magnetic field. Okay. So, and if we put a coil, if there is a change in magnetic field, there will be a change in electric field. That is what Faraday predicted, and that is what we are detecting using two coils present nearby. The design depends whether it is Helmholtz or Saddle, and it will decay to 0 because slowly the spin is going back to equilibrium. So, that is why this kind of signal is called a free induction decay. It is free because it is not been driven by any system now. It is induction because it is induced, yes, electromagnetic induction, and it is decaying back. Okay. So, we captured this FID, and this FID has information of different frequencies encoded in it. It totally depends upon the chemical environment or the way we are encoding information to it. So, it may have one frequency or two frequency or n number of frequencies, we do not know. So, how to decode that? We do that by just running a Fourier transform. So, if you Fourier transform this time signal, you get a frequency signal in which you see the spectrum. So, this is exactly what you were seeing over here. This is exactly what we are seeing over here. So, over here the system is a 2 qubit sample which is chloroform 13C level CHCl3, and I will explain how it forms as a 2 qubit of a system, and therefore, proton is 1 qubit and carbon 13C is another qubit. So, these two form as a 2 qubit system. There are millions of such molecules in the sample, but the qubit which is formed by proton and carbon. Okay. So, if we are having a state which is 1 0, then the spectrum that we should expect is like this. Okay. One should be down and one should be up. So, okay, I skipped a step, that is why it may appear a bit counterintuitive. So, the experiment has been done and we see the proton and the carbon spectrum. So, the essential difference is you see that there is some noise, that is why it is coming from the real system which is there in the 5th floor, and we see that it kind of matches exactly with what we had simulated. Okay. So, what have we done over here is we have explicitly illustrated that whatever we are learning in theory, blackboard, that we can actually visually see, simulate it as well as run in a real quantum computer, and also verify that whatever we are doing mathematically is also happening. Okay, it is not just mathematics. Number 2 thing is that since we are exposing some part of the hardware, so people see that okay, these wiggles are because of some other mathematical problem. So, that I will remove. So, but what I wanted to say is that since we are looking at some part of the hardware, the user sees that the output is not perfect. So, this line should not have been there, but it is there. This also should not have been there, it is there. This is because of the pulse imperfection, delay imperfections. You can never ever make a pure 90-degree gate, pure NOT gate or a pure Hadamard gate. There will be some imperfections. Yes, this is the actual output, and as a result that will give the students who are looking into it some perspective as to what a real quantum computer will give. Okay. Otherwise, it is just mathematical calculations.
In reality, we can say this is something like harmonics.
These are harmonics. These are harmonics, because that is what you are looking in the spectrum. So, why we have two such lines? That depends on the NMR system, and I can run you through quickly why we should be getting two lines for this system. But yeah, so basically this is what QuantUper is. It is a good tool to explain quantum algorithms, and simulation wise we can do as much as we can actually. We can go to
by looking at this, we have to predict that it is 1 0.
yeah. Not exactly. So, let us give an example. So, let us say that I want to teach DJ algorithm, just what we were looking in the beginning. So, if it is a balanced case and if I run one of the balanced, it is here, I am choosing DJ balanced, in which the first two have value 1 and the second two have value 0. It is a 2 qubit DJ balanced. So, all the hardware are limited to 2 qubit algorithms only. So, this is the circuit, okay. 2 Hadamard gate followed by a Z gate followed by 2 Hadamard gate again. So, you please note that we are not using any ancilla qubit over here, okay. So, what we have done is whatever kickback phase was there, we are encoding it as a phase, we are not encoding it as a C0 operation. It can be done, it is just another step of mathematical calculation. So, once we have explained this, we can simulate it and see that okay, in the balanced case we know that if it is constant we will get state 0 0. If it is balanced we can either get 0 1 1 0 or 1 1. In this case, in this particular case we are getting the state 1 0. Okay. So, now if I run this on the hardware, I will get two things which was not
hardware it is being done?
same NMR hardware.
That is, but you said it is 2 qubit computer.
I am doing this on 2 qubit only, right?
Somewhere
I had increased the number of qubits, but the moment I clicked this, it went to 2 qubit. Yeah. So, all the hardware submissions are 2 qubit examples. So, again it will take 2 minutes. So, okay, this time I will kind of give a very quick thing of what is. So, the initial density matrix or the thermal equilibrium density matrix of NMR is a highly mixed state. Okay. So, it is a mixture of 0 0 plus 1 0 plus 1 0 1 plus 1 1. Okay. So, they it is not in a pure state. So, the first step in any experiment is to create the pure state, and creation of a pure state is a set of pulse sequences. In this case, so okay, so this is the initial spectrum that you should be seeing. This is again simulated. So, if you have proton and carbon for a 2 qubit heteronuclear sample, this is the kind of spectrum that a person should see. Now, if you create a pseudo pure state using a set of pulses, it is written over here, but I will not expand because that will require more mathematics. So, after I run this pulse sequence, I have just simulated them over here. You get a pseudo pure state. So, the density matrix in NMR is a deviation density matrix. It's not, so therefore, the sum is 0. Okay. And so, once I have created the 0 0 pseudo pure state, what I am guaranteed that the population at 0 0 is maximized and everything else is equal. Okay. So, the spectrum for that should be like this. Yes. So, yeah. So, this is the kind of spectrum I should get, because there will be transition only from 0 0 to one of the two, one of the three. So, I will get 0 0 to 0 1 transition and 0 0 to 1 0 transition. So, these are the only two transitions or the harmonics that I will be seeing. So, this is a signature of a pure state, okay, 0 0 pseudo pure state. Now, if I add some x gate, then I will get something like this, and this is exactly what we were seeing also in Quantutor. It is still running. Okay. So, it was
nice to see that it is still running. अभी बच्चों को आदत ही नहीं है, तक किया कि result आता है.
Yeah. So, that is where I was coming to. So, so what happens in so if you look at the physical implementation of the quantum computers, then the major ones are, yeah, I will just like to show this slide. Oops. Yeah. So, the major ones are these. Sorry. So, you have superconducting qubits, you have trapped ions, you have photonic, and you have NMR. Okay. So, if you look at here, the the gate time and the coherence time. So, each of them have their own characteristic gate time. Okay. So, the gate time in superconducting qubits is of the order of microseconds, but the time for which the coherence exists is of the order of 10 to the power 4. Okay. So, if you just look at this, what we see is that once I have disturbed the system, okay, it will take some time to come back. Okay. And what is that time? So, the time is the time required for the spin to interact with the lattice and release all the I mean go back to the maximum entropy state. Okay. And in NMR that may run into seconds. So, if you see the gate time and the coherence time in NMR is very high. Okay. So, since that is the case, what happens is before we run another experiment, between two experiments or between two algorithm runs, we have to give something called a D1 delay, which currently in our system is 1 second. Since we have to run the experiment twice, one for proton and one for carbon, so it will be 60 second, 1 minute. So, therefore, we have to run it for 2 minutes. Okay. So, that also gives one more perspective that a person when he is working on a physical system, he should understand the physical system well before he can actually kind of go ahead and run any computation on it. Okay. Okay, so I hope it's done by now.
On that note, are we able to talk about the work that Harshit you have done to create the?
Yes. So, I will just show this and I was coming to that. That is why I was talking about the physical system. Yeah. Oops, I think this is done. Yeah. So, what we saw, this has gone. So, I will just simulate it again. So, we simulated 1100, right, DJ 1100 simulate. Yeah. So, this is the kind of spectrum that we were expecting and this is the density matrix that we were expecting. Okay. So, it should be 0010 in the diagonal. So, if you look at the experiments, the last one, this is a simulator. Sorry for clicking. Yeah. If you look at the experiment, this is what I had run and you see that the value of the diagonal elements is -15, -18, 72 and -38. So, that means there is a error. However, the population of 10 state is maximum. Okay. So, it kind of matches. So, we are still working on it, we have to move this whole thing in the front page, so that the student can see both the theory and the experiment together. Okay. And the spectrum wise also you see that after running the algorithm, when we were making the pseudo pure state, the error was less, but now I have added few gates. So, the error has increased and therefore, instead of getting 0.75 over here or 75 over here, I am getting difference and instead of getting -25 over here, I am getting almost -40. So, the error has increased because so as we increase the number of gates, most of the time it will accrue, but in NMR depending upon the phase in which we are applying the gates, it may balance each other out also. So, that is the way we actually design the pulse sequence. Okay. So, so this part was for actually showing what you can do. One more thing which I missed, that you can also look at the imaginary part. You can see both the real and imaginary part because the density matrix is a complex density matrix. Okay. Okay. So, what I had shown was that we were using this Bruker Fourier 80 to submit our experiments. So, what we had been doing actually, I and one of the interns over here, we were looking into kind of building this in house. So, what do we require? To do that, the major requirement is we have to have a magnet which is of around 1 to 1.5 Tesla. To do that, there are arrangements available called Hallback array. These are permanent magnets. So, what is the basic difference? So, if you look at a generalized NMR system, which Bruker sells. This is what is a research grade NMR system. So, this is a 500 megahertz spectrometer. It has a magnetic field of 11.7 Tesla. You need superconducting coils for that, because you cannot have permanent magnet with so high field. Okay. And this whole thing, it is a standard Avance 500. Its price is around, I think, 6 crores, something like that. So, what we have here is a simpler version. It is a 80 megahertz. So, it is around 1.2 Tesla, around 2 Tesla. Okay. These are permanent magnet. These are permanent magnets arranged in a Hallback array format, so that there is a homogeneous field at the center and almost zero field outside. So, once we have that magnet. So, designing the magnet is an important aspect of the project, because NMR is a very insensitive technique. Okay. So, the number of molecules which are there which contribute to the signal is very less, as a result of which, if the magnetic field is not homogeneous, then each molecule or each proton in sitting in different molecules will have a slightly different resonance frequency. So, therefore, when you Fourier transform it, you will get a very flat spectrum and you will not see any appreciable signal. So, therefore, we have to make a very, very homogeneous field. How to do that? There are two stages to it. One is the static shimming, which is basically adding very small pieces of magnet. We have to simulate and then add small pieces of magnet in this Hallback array, so that the homogeneity is improved. And the next is dynamic shimming, which is done by adding coils. So, there is a cylindrical structure and there are various forms of coils, which are basically the solution of the Bessel's function. It is solution of del square phi is equal to 0, the basic electromagnetic. Yeah. So, it comes out to be the spherical Bessel's function, and therefore, we have to add coils, so that if there is any change or slight difference in magnetic field, then we can change the current in the coil to generate an opposite magnetic field, so that the overall magnetic field is homogenized. This is called shimming. Okay. So, it can be automated, or it can be, mostly in earlier days we used to manually do it. Before we start any kind of experiment, we will spend around 3-4 hours just adjusting the current, so that my spectrum will have a line width of less than equal to 1 hertz. Okay. So, then we know that it is properly shimmed. This is the most difficult part of the project. Okay. So, once we are able to do this, then we require two things extra. So, one is the transmit chain and the other one is the receive chain. So, how do we excite the nuclear spins? I showed that we have to generate RF. So, the generation of RF, both are possible. So, Hallback array whether we can buy the magnets or we have to fabricate them. So, Hallback array, prefabricated Hallback array are available, which are slightly costly, around 3.5 lakhs for 1 Tesla. But we can also buy neobidium magnets, which are called N48SH. So, basically it is a grade of magnet which can sustain 1 Tesla at a wide temperature range. Okay. So, we can get those magnets and arrange them in the Hallback arrangement, so that we can get 1 Tesla. Doing that is a bit more tough, okay, because it requires a little bit more research. Okay. So, once the magnet has been built and the shim has been done, what we can do, then we have the transmit chain and the receive chain. So, for the generation of RF, we have identified Red Pitaya software defined radio, but that we do not need to stay in that only. There are so many SDRs which are available. Okay. So, mini circuits have one and Lime radio is there, but most of them are kind of slightly costly. But what is required is that we have to specifically look at the megahertz of at which it is generating the field, okay, or the frequency. So, in 1 Tesla, the frequency at which proton rotates or the precesses is around 40 megahertz, 42 point some megahertz. Carbon is around 10, fluorine is 40. Okay. So, these are all NMR active materials. So, if I have a sample like chloroform, which can give me 2 qubits, then I will need 2 channels and I should have the capability to have generate frequencies of the range of 40 megahertz and 42 megahertz. If sorry, for chloroform I need 10 megahertz and 42 megahertz. If I have a sample like this, yeah, if I have a sample like the right one C2F3I, in this fluorine form the 3 qubit, it is a homonuclear system. There are other problems with it, but let us not discuss that now. So, then I should have the capability of transmitting RF at 40 megahertz. Okay. We can have other samples like CHF-BR2. 13C level CHF-BR2 can also form a 3 qubit heteronuclear NMR computer for me, or NMR QIP for me, in which carbon, fluorine and proton can be used as the 3 qubits. Okay. So, therefore, what we need is the ability to generate those frequencies, that we can manage by using SDRs. Then once the output power of SDR is 0 dBm, okay, standard nomenclature. What we need to deposit on the sample, so the amount of sample that we have is in a 5 millimeter tube, we have around 2 inches of sample. So, it comes around 5 milliliter, something like that. Okay. So, we have to deposit 10 watt power on that. So, if we are depositing 10 watt power on that, we have to amplify this 0 dBm to 40 dBm. So, this is done generally in 2 stages. Okay. So, for that we can design our own amplifier which works, which has a linear range specifically at these frequencies, or we can buy also. So, if you are buying, they are available in mini circuits, they generally are a bit costly. The simple ones itself are 80-90,000, red pita is for around 90,000, 1 lakh. So,
you have to amplify from 0 to
yeah, 40 dBm. Okay. So, now that is one part, that is just the transmit part. So, once we have done that, so we will be able to deposit energy on the sample. So, then we have to receive it back, but while receiving we have to be very careful, because no power from the transmit should leak in the receive. So, we have to have a high quality TR switch, transmit receive switch. Okay. Why is it so? The reason being that the amount of power which is coming back from the sample is very, very low. So, therefore, we have to use a low noise amplifier which has a 40 dB of amplification. So, if any amount of current leaks from the transmit to the receive, even though it is in microampere, it will blow up the low noise amplifier. So, the low noise amplifier that not exactly, it will stop working. So, now this low noise amplifiers which we have identified, one is from Pasternak and it is around 1.5–2 lakhs. It is a very costly thing. Again, there is a scope of actually making a low noise amplifier in house which can do this kind of amplification without that much of cost. And also the low noise amplifiers are very costly because they also have this safety mechanism, okay, so that they are not they do not blow up. Okay. So, we have the transmit chain which is basically a set of attenuators and amplifiers. Attenuators are required because sometimes the output from one amplifier will not match the input of the other amplifier. So, you have to attenuate it to that level, yeah, otherwise it will saturate. So, similarly in the receive chain also we will have a set of amplifiers and attenuator, we get the signal back to the SDR. So, a red pitaya has 2 channels. Okay. So, if we buy one red pitaya, we can easily have 2 channel of output and input. Once we get the signal back, then we will use any kind of Python program to do the Fourier transform, do noise correction, do baseline correction, do phase correction. There are standard algorithms and there is a lot of research which can be done to get the spectrum. So, that will make our in-house NMR spectrometer which we can use to run any kind of quantum 2 qubit quantum algorithms. In future, let us say we want to add a 3rd qubit, then we can add another channel. Okay. So, one thing which I forgot to mention actually is that if you are buying a red pitaya SDR, then it comes with an internal clock, but if you are adding another channel to it, then we have to have an external clock, because when we are applying the pulses in proton and carbon, if I am applying on them together, it has to be exactly together, it has to match in nanoseconds, okay, because the pulses are in microseconds, that is the length of the pulse. So, to do that we have to have a clocking mechanism which has to come from outside, which will synchronize the RF pulses for all the 3 channels together. So, these are the electronics complications which are kind of involved, which I think is not that big because we have lot of expertise in electronics. Yeah, that is not a problem. The problem part is to get a very homogeneous field and design very nice both static and dynamic shimming. If we are able to do that properly, then I think people can easily overcome the electronics challenge and do the rest of it.
Dynamic means what?
Dynamic means that you have shim coils and you change the current to generate a field in a specific direction, so that it balances the. So, dynamic is actually dynamic, you can keep on changing it, and this I am calling the other one as static because those are very small magnets. Once fixed, it is there, you cannot change it.
Why is dynamic needed?
Dynamic is needed because the static shimming is never good enough, number one.
Why?
Because it is coarse, it is not fine, it cannot go to parts per million kind of smoothness. And number 2 is if there is a vibration, if there is some change in temperature, the field changes. It is temperature dependent, vibration dependent, lot of. So, therefore, we have to keep on shimming it again. So, like in this current setup that we have in the 5th floor, we I mean in most of the days I put a standard sample and run auto shimming overnight. If I do not do that, the next day I will get these fat lines. Okay. So, if I am doing auto shimming, then it always gives me around 1 Hertz lines. So, yeah, so that was it. So, I would encourage you to explore the Quantuper and to see whether it can be used for actual teaching, and I think it can be. And also I would like to add, we will be adding algorithms to it, and if you think that we need to for demonstration purpose, if we need to add few more algorithms, we are open to add it. You can get back to us, but in future we will anyway be adding more algorithms to it. Okay, that is all I had. So,
Yesterday I did, I did mention that this was a potential project.
yeah.
And one of the suggestions from somebody was we all have a capex budget. So if you share the bill of materials,
Yeah.
that can probably already be included. There was enthusiasm to build it locally.
Yeah, yeah.
So if you already have that,
Yeah,
if you share it, then they can include it.
So, offhand we think that it is, I will share the whatever is required, but offhand estimate is around 10 to 12 lakhs for building it up. The thing is, if what is really challenging and interesting is if you are able to build all those things in house, then it can be brought down, and yeah, then it will become very feasible also. So, okay, thank you. I will stop it now.
This should interest students in general, being interdisciplinary.
Yeah.
It's a very good learning opportunity also.
Yeah.
It would be good for students to participate as a team then
Yes.
across multiple departments.